What happens when an object from beyond our solar system enters our cosmic neighbourhood? On April 1st, 2020, the Asteroid Terrestrial Impact Last Alert System, better known as ATLAS, detected a faint moving point of light. Its speed was extraordinary, nearly 60 kilometers per second relative to the Sun, far greater than any asteroid bound by solar gravity. The object, designated 3I/ATLAS, carried a hyperbolic trajectory, meaning it was not from here. It came from interstellar space, just like the enigmatic Oumuamua discovered in 2017 and the comet Borisov in 2019. But this time, there was something different. Its path was steep, cutting through the solar system at an angle no comet or asteroid should naturally take. Initial orbital solutions confirmed the eccentricity exceeded 1, an unmistakable sign of interstellar origin. At its closest, it would pass within 1 astronomical unit of the Sun, roughly Earth's distance, before being slingshotted back into the darkness. Yet before it even neared perihelion, astronomers saw something they didn't expect. Spectral analysis from major observatories, including the Lowell Discovery Telescope and instruments in Hawaii, revealed a composition that didn't match any typical cometary pattern. The reflectivity was inconsistent. The light curve suggested fragmentation, but the timing and energy were unusual. And then came the brightening event, an unexpected surge in luminosity that models could not fully explain. Was this simply a volatile-rich comet responding to solar heating, or was something far more complex unfolding? The arrival of 3I/ATLAS opens questions about the nature of matter beyond our star, the frequency of these encounters, and the dangers they might pose. If one fragment altered course even slightly, what could happen? As observations piled up, so did the uncertainties. The detection of 3I/ATLAS was not a sudden dramatic flash across the sky, but rather a faint, barely noticeable signature buried in the data streams of automated surveys. ATLAS, the system that bears its name, was designed to protect Earth by scanning for near-Earth objects that could pose a threat. Yet, on April 1st, 2020, the data flagged something entirely different. The object was faint, but its motion revealed an anomaly that could not be ignored. Unlike typical comets or asteroids bound to the Sun, this body had a trajectory that escaped gravitational confinement. Its calculated orbital eccentricity exceeded 1, a value that signifies an open-ended journey, an object that did not belong to our solar system and would never return once it passed through. The first orbital determinations showed that 3I/ATLAS approached from a direction far from the plane of the ecliptic, entering the solar system on a hyperbolic orbit inclined at an unusual angle. For reference, the majority of solar system bodies orbit roughly along the same flattened disk. The ecliptic, shaped by the Sun's formation billions of years ago. This newcomer, however, plunged in from high above, suggesting an origin in the interstellar depths, perhaps even from the gravitational sphere of an entirely different star. Its inbound velocity before encountering the Sun's gravity was estimated at around 30 kilometers per second, already faster than any bound comet could achieve. By the time it reached the inner solar system, solar attraction accelerated it to nearly 60 kilometers per second, a speed that allowed no possibility of capture. At this point, astronomers had a list of immediate priorities. They needed to track its motion precisely, refine the orbit, and obtain as much observational data as possible before it slipped away forever. A body arriving from interstellar space is rare. Before 2017, no confirmed example existed. Then came Oumuamua, a cigar-shaped object that baffled researchers with its non-gravitational acceleration and lack of a visible coma. 2 years later, comet Borisov appeared, a more conventional icy body but still alien in origin. 3I/ATLAS, named as the third confirmed interstellar visitor, was expected to behave in ways broadly consistent with a cometary nucleus. Volatile ices sublimating as it approached the Sun, perhaps fragmenting as thermal stress increased. Yet early observations unsettled that expectation. When telescopes captured its light, the brightness curve did not align with predictions for an object of its estimated size. The variation suggested an elongated or highly irregular shape, or perhaps multiple fragments tumbling together. Some models indicated a nucleus tens of meters across, while others suggested a much larger object partially disintegrating. This ambiguity in size and structure was troubling. If it were breaking apart so far from the Sun, what forces were driving that process? Solar heating typically dominates cometary disintegration, but at the distances where fragmentation seemed to begin, energy input was still relatively low. As data continued to arrive from observatories across the globe, one trend became clear. 3I/ATLAS was brightening at an unexpected rate. In cometary science, brightening can indicate the release of gases and dust, increasing the object's reflective area. But the magnitude of the increase exceeded standard activity patterns, especially for an object that was still far from perihelion. Researchers considered the possibility of hypervolatile ices, such as carbon monoxide or carbon dioxide, sublimating at much lower temperatures than water ice. Such substances could drive activity in the outer regions of the solar system, yet even this explanation felt incomplete when the brightening accelerated into what appeared to be an outright surge. Astronomers began to compare 3I/ATLAS with Borisov, whose behaviour was more predictable. Borisov had shown gradual, consistent outgassing, a classic cometary signature. 3I/ATLAS, by contrast, seemed erratic. This raised questions about its internal composition and structure. Was it a loosely bound aggregate of dust and ice, highly fragile and susceptible to even minor thermal gradients? Or was there something unusual about its history, a journey through extreme conditions that altered its physical integrity? If interstellar objects form in other star systems, they could experience environments our own comets never encounter. Supernova shockwaves, radiation from massive stars, or violent planetary ejections. Each scenario could produce bodies with exotic chemistry and physical properties unlike anything in the solar system. Fragmentation soon became undeniable. High-resolution imaging suggested that the object had broken into multiple components, each following slightly divergent paths. This process began well before it reached its closest approach, an unusual timing compared to most solar system comets, which often survive until they encounter intense heating near the Sun. The early onset of disintegration could indicate extreme internal weakness. It might also suggest that internal stresses accumulated over millions of years in interstellar space, finally releasing as the body experienced new gravitational and thermal forces. At this stage, the scientific urgency shifted. Researchers realized that if 3I/ATLAS continued to fragment, it could disperse material across a wide arc of space. While the main trajectory posed no threat to Earth, fragments could behave unpredictably. Even small pieces, if perturbed by gravitational interactions with planets, could alter course. Though the probability of an Earth impact was extraordinarily low, the mere possibility prompted detailed simulations. Planetary defense models consider such scenarios seriously, even when the risk appears negligible, because the consequences of a miscalculation could be catastrophic. Simulations conducted by multiple research teams focused on the gravitational environment through which 3I/ATLAS would pass. As it entered the inner solar system, it would encounter the combined influence of Jupiter, Saturn, and other planets, as well as solar radiation pressure. Each factor could nudge fragments slightly, altering their outbound paths. Most fragments would likely disperse harmlessly into the outer regions, but a small subset of trajectories intersected with planetary orbits in the far future. None indicated a near-term collision, but the calculations underscored the complexity of predicting the fate of interstellar debris. The case of 3I/ATLAS also raised a broader question. How many similar objects cross our solar system undetected? Surveys have only recently achieved the sensitivity to detect small, fast-moving bodies from interstellar space. If 3 confirmed interstellar objects appeared within just a few years, Oumuamua, Borisov, and Atlas, it suggests a much larger population. Statistical extrapolation indicates that thousands, perhaps millions, of such objects could traverse the galaxy, ejected from their home systems during planetary formation or other gravitational disturbances. These travelers could represent the most common class of material exchanged between stars, making them critical to our understanding of cosmic chemistry and even the origins of life. Yet despite their scientific importance, these objects pose challenges to observation. Their hyperbolic paths mean they appear suddenly, move rapidly across the sky, and leave quickly. Capturing them requires early detection and rapid coordination among observatories. In the case of 3I/ATLAS, its discovery came early enough to allow meaningful study, but the window was still short. Once past perihelion, its velocity would carry it back into interstellar space, beyond the reach of even our most powerful telescopes. This fleeting nature gives every observation added weight, every data point a chance to reshape our understanding of the galaxy's material exchange. Still, the most perplexing aspect of 3I/ATLAS was not simply its rarity or its fragmentation, but the implications of its composition. Spectroscopic analysis revealed elemental and molecular patterns broadly consistent with cometary material but with anomalies in isotope ratios. These variations could reflect formation in an environment unlike our solar system, perhaps around a star of different metallicity, or in a region enriched by previous generations of stellar evolution. Such findings are not mere curiosities. They inform models of planet formation, chemical evolution, and the likelihood of organic compounds spreading between star systems. The idea of panspermia, life or its building blocks travelling across interstellar distances, remains controversial, but objects like ATLAS provide a tangible mechanism for material transfer. If organic molecules reside within these bodies, they could be shielded from radiation for millions of years inside protective layers of ice and dust. The interstellar void is harsh, but not entirely sterilizing under certain conditions. Thus, every interstellar comet carries not just rock and ice, but potentially the molecular signatures of alien worlds. Whether life could survive such a journey is uncertain, but the chemistry that precedes life almost certainly can. This possibility reframes interstellar objects from mere curiosities to vectors in a vast galactic network of material exchange, a process that may operate over billions of years and across unimaginable distances. As scientists ponder these possibilities, one question becomes increasingly pressing. How prepared are we for the next encounter? Interstellar objects do not announce their arrival. They emerge from darkness, traverse the solar system at staggering speed, and vanish again. Our ability to detect, study, and, if necessary, respond to such visitors remains limited. 3I/ATLAS was an opportunity, but one we could not fully exploit. No spacecraft was dispatched to intercept it. No probe sampled its material. The event passed, leaving only observations and models. Next time, will we be ready? Or will another fragment from another star slip past us, carrying secrets we cannot reach? Yet even as these strategic questions linger, the physical reality of 3I/ATLAS continues to demand analysis. Its brightness surge, its fragmentation, its anomalies in composition, all point to processes we do not fully understand. And where understanding falters, speculation begins. Could tidal forces alone account for the early breakup? Was the internal structure riddled with weaknesses from cosmic radiation or past collisions? Or does the explanation lie in chemical processes unique to environments we have never observed? The answers remain elusive, but the implications are profound. For if a single object can challenge so many assumptions, what will 100 such discoveries reveal? And as our instruments improve, those discoveries are not hypothetical, they are inevitable. The study of 3I/ATLAS does not end with its departure from the solar system. Its data, archived and analysed, will continue to shape theories for decades. But in the moment of its passage, in that brief encounter with an emissary from another star, the questions it raised far outweighed the answers we could provide. And that imbalance is what drives the next phase of inquiry, to understand not only what 3I/ATLAS was, but what it means for the future of interstellar science and the hidden architecture of our galaxy. But one question remains unanswered. If an interstellar object can fragment so easily, scattering material across the inner solar system, what is the true scale of risk from such events? And more importantly, could something far larger, something capable of reshaping entire worlds, be following a similar path even now? The idea of risk from interstellar objects has long been considered negligible. Their velocity, the vastness of space, and the sheer improbability of alignment with Earth's orbit seem to guarantee safety. But 3I/ATLAS forced researchers to revisit that assumption. Its fragmentation pattern was not a slow shedding of dust, but a rapid and violent disintegration, producing significant debris in a relatively short time span. This is important because high-velocity fragments, even if small, carry enormous kinetic energy. At speeds approaching 60 kilometers per second, an object just tens of meters wide would release energy equivalent to multiple nuclear detonations upon impact with Earth. The probability remains extremely low, but the consequence of even a single collision demands attention. To understand why these fragments matter, we must examine the mechanics of interstellar trajectories. When an object enters the solar system on a hyperbolic path, it interacts gravitationally with the Sun and, to a lesser extent, the planets. These encounters can alter fragment trajectories subtly but meaningfully. A small deviation near a massive planet like Jupiter could redirect a fragment toward a new path, potentially one intersecting with Earth's orbit. Planetary defense simulations modeled scenarios based on the estimated dispersion of ATLAS debris. Most outcomes showed the material dispersing into heliocentric orbits that pose no danger. However, a small fraction of simulations indicated possible Earth-crossing paths centuries from now, rare but not impossible. These long-tail probabilities are what planetary defense experts call non-zero risks, events too improbable for immediate alarm but too consequential to dismiss. Such considerations highlight a critical difference between interstellar objects and traditional near-Earth objects. Our catalogue of asteroids and comets within the solar system is growing increasingly complete for bodies larger than 1 kilometre. We can predict their motions decades, even centuries, in advance. Interstellar visitors, by contrast, appear with little warning and depart swiftly, leaving minimal time for observation and no opportunity for intervention. Their speed renders current deflection strategies ineffective. A nuclear detonation or kinetic impactor requires years of preparation and proximity to the target. With interstellar objects, by the time we detect them, they're already inbound and often past their point of closest approach before serious planning begins. 3I/ATLAS exemplifies this dilemma. Detected in April 2020, it was already on its inbound trajectory at high speed. Even if a probe had been pre-designed and ready for launch, the timeline for interception would have been measured in months, not years. The engineering and logistical challenges would have been immense and the cost prohibitive. Yet this scenario is not theoretical forever. Future missions like the proposed Comet interceptor aim to address exactly this problem. A spacecraft placed in a standby orbit, ready to sprint toward an incoming object at short notice. But even these ambitious plans are calibrated for long-period comets, not hyperbolic interstellar bodies moving at tens of kilometers per second. To rendezvous with such an object would require unprecedented propulsion systems, rapid mission planning, and international coordination on a scale not yet demonstrated. The urgency to prepare for such encounters grows as evidence accumulates that these objects are not exceedingly rare. The discovery of 3 confirmed interstellar objects in just a few years, Oumuamua in 2017, Borisov in 2019, and Atlas in 2020, suggests that many more pass unnoticed. Detection capability has improved, but it is still far from comprehensive. Surveys like Atlas, Pan-STARRS, and upcoming projects such as the Vera Rubin Observatory will increase our ability to spot these fast-moving interlopers. Even so, most will remain fleeting, observed only through remote sensing, their physical secrets inaccessible. While impact risk drives public concern, the scientific implications are equally compelling. Interstellar objects carry with them the chemical and physical signatures of their origin systems. Studying them offers a direct window into planetary formation processes beyond the Sun. For instance, isotope ratios in ATLAS hinted at subtle differences from typical solar system comets, suggesting formation in a region with distinct chemical enrichment. These anomalies provide empirical constraints on models of galactic evolution. They tell us that planet formation across the galaxy is not uniform, that local conditions imprint unique signatures on the bodies they produce. Each interstellar object is therefore a messenger from a distant stellar nursery, carrying evidence of processes we cannot otherwise observe. The fragmentation of ATLAS also informs our understanding of mechanical strength in icy bodies formed under alien conditions. Comets in our solar system often fragment near the Sun, where heat drives rapid sublimation. Atlas began to break apart much earlier, raising questions about its internal structure. Perhaps it was composed of loosely bound aggregates, held together by minimal cohesive forces, making it vulnerable to even modest heating. Alternatively, It may have accumulated structural weaknesses during its long interstellar journey, thermal stresses from passing near other stars, impacts with micrometeoroids, or internal cracking from cosmic ray exposure. Over millions of years, these stresses could render an object so fragile that a modest change in temperature triggers catastrophic failure. If this interpretation is correct, then most interstellar objects might not survive close approaches to stars. They would disintegrate, scattering material across interplanetary space, adding to the dust and small debris that permeates stellar systems. From a planetary defense perspective, this is both reassuring and concerning. Reassuring because large intact bodies may be less common. Concerning because fragmentation produces swarms of smaller objects, each a potential hazard if redirected by gravitational interactions. In this sense, the threat from interstellar visitors is diffuse, not concentrated, a statistical background risk rather than a singular catastrophic event. But let us imagine the opposite scenario. Suppose an interstellar object arrives not as a fragile comet, but as a dense rocky body hundreds of meters across, a shard of an alien planet's crust, or the remnant core of a shattered moon. At 60 kilometers per second, such an object would strike with energy far exceeding the Chicxulub impactor that ended the age of dinosaurs. The devastation would be global, the consequences unimaginable. Could such an event happen? The probability is vanishingly small, yet not zero. Galactic dynamics eject countless bodies during planetary formation. Most wander in deep space indefinitely, but given enough time, some will intersect with other stellar systems. Over billions of years, the odds, however remote in human terms, become significant on cosmic scales. This scenario underscores the limitations of our current planetary defense paradigm. We focus on threats within the solar system, where predictability and lead time make intervention feasible. Interstellar hazards occupy a different category, rare, unpredictable, and effectively unstoppable with present technology. Addressing this class of risk would require transformative advances, propulsion systems capable of rapid acceleration, detection networks that extend far beyond the current reach, and perhaps even autonomous interceptors pre-positioned in deep space. These are not projects for decades, but for centuries, if humanity persists long enough to undertake them. For now, our strategy remains observational. We track what we can, model the probabilities, and refine our understanding of the processes that produce these objects. The lesson of 3I/ATLAS is that knowledge alone may not prevent catastrophe, but ignorance guarantees vulnerability. By studying these rare visitors, we not only expand our scientific horizons, but also lay the groundwork for a future in which preparedness extends beyond the confines of our own solar system. As the focus on risk calculations deepens, another question emerges. What about the chemical and biological implications of these interstellar fragments? If Atlas carried complex organic molecules, and evidence suggests it did, then its disintegration scattered that material into our solar system. Could such fragments eventually fall to Earth, delivering compounds forged under alien suns? The answer may already be written in our planet's history. Meteorites of uncertain origin, bearing amino acids and other prebiotic molecules, have long fueled speculation that life's raw ingredients arrived from space. Interstellar objects multiply that possibility across galactic scales. Each one is a capsule of chemistry, a record of processes billions of years and light years removed from our own. But this speculation invites another, more provocative thought. What if some interstellar objects are not entirely natural? The idea gained traction after Oumuamua's unexplained acceleration and unusual shape led some researchers, including Avi Loeb of Harvard, to propose non-gravitational forces, possibly even artificial origin. Most of the scientific community remains skeptical, favouring natural explanations like outgassing or radiation pressure. Yet the question lingers because our sample size is tiny and our understanding incomplete. If we encountered an object with unmistakably artificial features, the implications would surpass any scientific discovery in history. It would mean that across the void, intelligence exists or once existed, capable of constructing and launching artifacts into interstellar space. Could a TLAS, in its fragmentation and anomalies, have concealed such a story? The data we have suggests no, but the data we lack leaves room for wonder. And so, as Atlas fades into the dark, outbound on its eternal trajectory, we are left with fragments of knowledge and an abundance of questions. Each fragment invites deeper inquiry into the forces shaping our galaxy, the risks we face, and the possibilities we scarcely dare to imagine. Yet this evidence raises new scientific questions. If interstellar objects are carriers of chemistry, risk, and perhaps even intent, what role do they play in the grand architecture of the cosmos? And what happens when the next one appears? Faster, larger, stranger than anything we have seen before. The next interstellar visitor may already be on its way. Statistically, based on current detection rates and improvements in observational technology, astronomers expect another within the next decade, perhaps even sooner. But what form will it take? Will it resemble a comet like Borisov, a fragmenting object like Atlas, or something as anomalous as Oumuamua with its elongated shape and unexplained acceleration? Each of these cases shattered expectations, proving that interstellar objects are not a uniform class but a diverse population, shaped by countless environments across the galaxy. That diversity presents both a challenge and an opportunity. A challenge because predicting behavior becomes nearly impossible, and an opportunity because every new object is a probe from a different region of space, a messenger bearing clues from distant stellar nurseries. To prepare for the next encounter, astronomers are betting heavily on future survey projects. The Vera Rubin Observatory, with its legacy survey of space and time, promises an unprecedented ability to detect faint, fast-moving objects at the outer edges of the solar system. Unlike current systems which cover the sky in segments and often miss rapid movers, Rubin will scan vast portions of the sky repeatedly, increasing the chances of early detection. But early detection alone will not solve the fundamental issue. Interstellar objects travel so fast that by the time we see them, they are already on an exit trajectory. The only realistic strategy for detailed study is to have a spacecraft on standby, ready to intercept. The European Space Agency's Comet Interceptor mission represents the first step toward this goal. Scheduled for launch later this decade, it will park at the Sun-Earth Lagrange point L2, awaiting an inbound comet or other suitable target. When such an object is detected, the interceptor will detach and accelerate to meet it, conducting close-range observations. But even this ambitious plan is optimized for comets originating within the solar system, not interstellar bodies moving at extreme velocities. To match an object like Atlas would require delta V beyond the capacity of current chemical propulsion, pushing us toward technologies that remain experimental. Solar sails, nuclear thermal propulsion, or even concepts like fusion drives. Until these systems mature, close encounters will remain rare, dictated by luck and timing rather than readiness. Still, the prospect of intercepting an interstellar object is not science fiction. In fact, every major space agency understands the potential payoff. A direct sample return from such an object would be transformative, offering unfiltered evidence of chemistry from another star system. Unlike meteorites, which endure atmospheric entry and terrestrial contamination, an untouched fragment would preserve pristine molecular structures, isotopic ratios, and mineralogy. Analyzing these materials could confirm or refute theories about panspermia, reveal exotic compounds unknown in our solar system, and provide insight into the early stages of planet formation across the galaxy. But what if the next interstellar visitor is not a fragmenting comet or a harmless shard? What if it is large, cohesive, and on a trajectory that intersects Earth's orbit? The odds are vanishingly small, but the consequences would be existential. At speeds exceeding 50 kilometers per second, an object even a kilometer across would release energy orders of magnitude beyond the most catastrophic asteroid impacts in Earth's history. Unlike a near-Earth asteroid, which offers years or decades of warning, an interstellar impactor might appear only months before collision. No deflection strategy exists for such a scenario. Our current mitigation concepts, gravity tractors, kinetic impactors, nuclear explosives, rely on long-lead times to impart subtle velocity changes. Against an inbound interstellar object, these methods would fail. This reality forces a sobering acknowledgement. We are effectively defenseless against certain classes of cosmic hazards. The only practical response to an imminent interstellar impact would be evacuation or underground sheltering, measures that might preserve fragments of civilization but not prevent global devastation. Fortunately, the probability remains extremely low, perhaps on the order of one such event every few billion years for Earth. Yet probability does not erase possibility, and as detection systems improve, the day may come when we confront that reality not in abstract models but in urgent mission planning. Beyond the physical threat, there is another dimension to these encounters, the philosophical and existential questions they raise. Interstellar objects remind us that the solar system is not isolated but part of a dynamic galactic environment. Material flows between stars, carrying elements, compounds, and possibly even precursors to life. If life emerged on Earth through a chain of chemical accidents, could those accidents have been influenced by substances delivered from another system? Could amino acids or nucleobases formed around a distant star have seeded our early oceans? And if so, is life across the galaxy linked by a common chemical ancestry, distributed by countless wandering fragments over billions of years? Some scientists argue that panspermia, while speculative, is consistent with observed chemistry. Complex organic molecules form readily in interstellar clouds, survive in cometary nuclei, and can endure ejection from planetary systems under the right conditions. Interstellar comets like ATLAS provide a mechanism for delivery, albeit one that spans immense timescales. If even 1 in a million such objects carried viable prebiotic material that reached a habitable planet, the cumulative effect across the galaxy could be profound. This vision transforms interstellar objects from passive debris into active participants in a cosmic process of chemical evolution, perhaps even biological dissemination. Yet the data from ATLAS, though limited, also reminds us of the difficulty of confirming these ideas. We observed only its light, measured only its spectra, and tracked its path for a fleeting moment before it vanished into the void. Our instruments teased out clues, volatile signatures, isotope ratios, but the core secrets remain locked away, carried beyond reach at a speed no spacecraft could match. This frustration fuels the drive for readiness, the determination to seize the next opportunity. Each detection is not just an astronomical event, but a test of our technological and scientific ambition. As we consider the next encounter, one question persists. What if the anomalies we see, unexpected brightening, unusual trajectories, are not merely natural quirks but signs of something more? After Oumuamua's unexplained acceleration, some researchers entertained the possibility of artificial origin, not as a conclusion, but as a hypothesis to be tested. The idea remains controversial, yet its implications are staggering. If a future object displays unmistakable artificial characteristics, a geometric shape, controlled maneuvers, what would that mean for humanity? Such an event would redefine our place in the cosmos, collapsing the distance between speculation and reality. Until that day, we continue to look outward, scanning for faint points of light against the black sky, knowing that each could be a fragment of another world, a traveller from a distant sun, or a harbinger of questions we are not yet prepared to answer. The story of 3I/ATLAS is not one of finality but of beginnings, the start of an era in which the galaxy itself becomes part of our observational reach, and in which the unknown is not an abstract concept but a moving target on a hyperbolic path. Yet, as technology advances and detection improves, another unsettling thought emerges. If interstellar objects are so common, and if their diversity includes both harmless ice balls and dense rocky cores, then the range of possible encounters spans from scientific curiosity to existential threat. We have seen the benign, we have glimpsed the fragile, but what lies at the other extreme? Could a body larger than any known asteroid, forged in the furnace of another star, be hurtling toward us even now, invisible against the cosmic background until it crosses the threshold of detection? If so, how would we respond? And what does that possibility reveal about the vulnerability and resilience of a species confined to one small planet in an unending sea of stars? If that possibility seems distant, consider what recent discoveries imply. When Oumuamua was first detected, its hyperbolic path revealed the existence of interstellar objects beyond theoretical speculation. Then came Borisov, confirming that these travellers are not rare anomalies but likely common visitors. 3I/ATLAS added yet another data point in rapid succession. Statistically, this means the galaxy is alive with motion, billions of fragments ejected from forming planetary systems, endlessly migrating between stars. The solar system is not a closed system, but a permeable region in a constant exchange of material with interstellar space. That dynamic changes how we think about planetary defense, cosmic chemistry, and even the origins of life. Planetary defense specialists are recalculating risk models in light of this reality. Before 2017, the focus was almost exclusively on near-Earth asteroids originating within the solar system. Those bodies, while dangerous, move on predictable orbits. We can map them years or decades ahead and develop deflection strategies. Interstellar objects present a different category altogether. They arrive unannounced, at velocities far exceeding typical asteroids, and depart quickly, leaving no margin for error. An interstellar object on a collision course would likely be detected only months, perhaps weeks, before impact. And given their speed, often above 50 kilometers per second, any attempt to deflect them would require technology far beyond our current capabilities. How much energy would such an impact deliver? Consider a rocky body 200 meters across, traveling at 55 kilometers per second. Its kinetic energy would be on the order of 2,000 megatons, roughly 40 times the combined explosive yield of every nuclear weapon ever detonated on Earth. At 1 kilometer, the energy release would dwarf the impact that ended the age of dinosaurs, producing a global catastrophe: firestorms, tsunamis, climate collapse. The good news is that the probability of such an event in any given century is astronomically low. The bad news is that it is not zero, and time turns even the smallest probabilities into certainties over cosmic scales. That is why detection remains our first and most critical line of defense. The Vera Rubin Observatory, slated to begin full operation soon, represents a leap forward. Its 8.4-meter mirror and wide field of view will scan the entire visible sky every few nights, dramatically improving our ability to detect faint, fast-moving objects. Coupled with improved data processing and machine learning algorithms, Rubin could alert us to interstellar visitors much earlier than before, yet early detection is only the beginning. What do we do when detection is followed by confirmation of a threat? With near-Earth asteroids, we have contingency plans: kinetic impactors, gravity tractors, nuclear devices. With an interstellar impactor, none of those are viable given current propulsion limits. Even nuclear options, while theoretically powerful, would require decades of preparation we do not have. This leads some scientists to advocate for a different strategy: readiness missions placed in heliocentric orbits, capable of rapid acceleration toward inbound objects. Such systems might use advanced propulsion, solar sails that leverage the sun's energy, electric propulsion powered by compact reactors, or in the long term, fusion-based engines. These concepts are still experimental, but their development may become essential if interstellar encounters continue to rise. Without them, every visitor remains beyond our reach, both as a potential threat and as a scientific treasure. Scientific value cannot be overstated. A single intercepted interstellar object could revolutionize our understanding of planetary formation across the galaxy. The isotopic anomalies detected in ATLAS hint at processes occurring in stellar nurseries far from the Sun. Some measurements suggest enrichment from nearby supernovae, indicating that ATLAS formed in a region shaped by violent stellar deaths. Such details illuminate the diversity of planetary systems, the distribution of heavy elements, and the mechanisms by which material circulates between stars. These insights feed into broader questions. How common are Earth-like planets? How often do conditions suitable for life arise? And are the chemical pathways that lead to biology universal or rare? This last question bridges science and philosophy. If interstellar objects can deliver organic molecules across vast distances, then the galaxy may function as a chemical network, with comets and asteroids acting as carriers. Laboratory experiments and meteorite studies show that amino acids and nuclear bases can survive the harshness of space when shielded within rock or ice. Over millions of years, such fragments could hop between stars, seeding planets with the raw ingredients for life. While this does not imply that life itself travels intact, it strengthens the case for panspermia as a contributor to prebiotic chemistry. In that sense, every interstellar object is more than a rock. It is a messenger, not of intelligence, but of possibility. Yet intelligence remains an unavoidable speculation. Oumuamua's peculiar properties, its elongated shape, its unexplained acceleration, sparked hypotheses that, while controversial, cannot be entirely dismissed. Avi Loeb's suggestion that it might be a fragment of alien technology drew criticism, but it also forced the scientific community to confront a difficult truth. With so few observations, ruling out artificiality is nearly as hard as proving it. Atlas, while more consistent with a natural comet, still displayed anomalies in fragmentation timing and brightness evolution. Could these be explained by unfamiliar chemistry, or do they hint at processes beyond natural models? Most evidence supports the former, yet the latter remains a provocative, if remote, possibility. Imagine the implications if a future interstellar object showed clear artificial features, regular geometry, unusual reflectivity, or controlled maneuvers. It would constitute the most significant discovery in human history, eclipsing every previous scientific achievement. The realization that intelligence exists, or once existed, beyond Earth would reshape not only science but culture, philosophy, and geopolitics. But such a discovery would also raise urgent questions. Who built it? Why was it launched? How long has it been travelling? And what does it mean for our future in a galaxy that suddenly feels far less empty? Until that day, we operate in a realm of limited data and expansive inference. 3I/ATLAS, like its predecessors, gave us a fleeting glimpse, a few weeks of observation, a handful of spectra, and an enduring mystery. It confirmed that interstellar objects can fragment dramatically, that their chemistry may diverge from solar norms, and that their frequency is higher than once imagined. But it also left us with unresolved questions about origin, structure, and long-term impact risk. Each answer spawns more questions, driving a cycle of inquiry that pushes the boundaries of both astronomy and engineering. One of those questions concerns the unseen population. If 3 have been detected in just a few years, how many pass through undetected in the centuries before modern surveys? How many will pass through in the centuries ahead? And among them, what is the distribution of size, composition, and velocity? Are most fragile and short-lived like Atlas, or are some massive and durable, capable of surviving repeated stellar encounters without significant alteration? Statistical models are in their infancy, constrained by tiny sample sizes, but they all converge on one point. The solar system is not an isolated domain. It is porous, threaded by countless trajectories of bodies born under alien suns. As we deepen this realization, another truth becomes unavoidable. In the vast exchange of material between stars, Earth is not just a passive recipient. Over billions of years, fragments from our system have likely escaped into the interstellar medium, carrying with them isotopic signatures, minerals, and perhaps even microbial life. If so, then the question of life elsewhere is not merely about origin but about continuity. The galaxy may not only harbour life in isolated oases, but sustain a slow, diffuse migration of its building blocks across unimaginable distances. Interstellar objects are the couriers of that migration, silent, indifferent, and relentless. And so we return to the central question. What's the worst thing that could happen? Not a fragment of Atlas brushing Earth's atmosphere, nor even a kilometre-wide rock striking without warning, though that would end civilizations. The true worst case is complacency, failing to prepare, to study, to learn from these rare windows into a broader cosmic system. Because the next visitor will come. Whether it brings knowledge, danger, or both depends not on its nature but on our readiness. The hyperbolic path of ATLAS is more than a trajectory. It is a reminder that the unknown does not wait for us to understand it. It arrives, unannounced, at 60 kilometers per second and vanishes into the dark, leaving us with data, questions, and the uneasy certainty that another is already inbound. But what if the next one isn't just another comet? What if its speed, its size, or its composition defies every model we have? What if it carries not just matter, but meaning? And if that meaning is beyond our comprehension, are we prepared to face it? There is one dimension we have yet to examine: long-term dynamical effects. When an interstellar object like 3I/ATLAS cuts through the solar system, it does not merely pass unnoticed through the gravitational field of the planets. Each close approach, no matter how fleeting, creates a measurable but complex gravitational exchange. These perturbations may seem negligible compared to the massive architecture of planetary orbits, but over astronomical timescales, cumulative interactions from countless such objects could alter the stability of small bodies within the system. Consider the Oort cloud, that vast reservoir of icy fragments extending tens of thousands of astronomical units from the Sun. Its population is thought to number in the trillions, each object delicately balanced between solar gravity and the galactic tide. An interstellar visitor on a grazing trajectory through this cloud could dislodge hundreds, even thousands, of bodies, sending them inward toward the Sun. Some might intersect Earth's orbit. While most would remain harmless, the probability of an eventual impact rises subtly with every perturbation. In this sense, interstellar objects act not only as direct threats, but as long-term catalysts for increased cometary traffic. A single close passage could, millions of years later, translate into a mass extinction. This brings us to the statistical models used to estimate such risks. Current frameworks rely on simulations with initial conditions derived from limited observational data. Each new detection recalibrates those assumptions, narrowing the range of uncertainty but also exposing gaps in our understanding. For instance, Atlas exhibited an active phase earlier than predicted, likely due to super-volatile compounds such as carbon monoxide or carbon dioxide sublimating far from the Sun. This behavior complicates predictions of when and where an object might fragment, a key factor in hazard assessment. Fragmentation alters both the cross-sectional area and the radiation pressure dynamics, which in turn can affect trajectory. Even minor changes in course become significant at interstellar speeds, creating challenges for tracking and modelling. Another challenge lies in composition. While initial spectroscopic analysis of ATLAS suggested similarities to carbonaceous comets, certain absorption features hinted at unusual ratios of volatile species. Some researchers proposed that its ice contained exotic compounds formed under conditions not replicated in the early solar nebula, perhaps in a protoplanetary disk near a different type of star, or in a system enriched by the ejecta of nearby supernovae. If true, then interstellar comets are not just foreign bodies but geological time capsules, preserving environments that no longer exist. Extracting and analysing such material would offer insights into stellar evolution and chemical distribution across the galaxy. But capturing an interstellar object remains a formidable challenge. To match velocities with something travelling at 50 or 60 kilometers per second requires propulsion systems far beyond chemical rockets. Concepts like solar sails, electric propulsion, and even nuclear pulse drives have been discussed in technical literature, but none have been deployed at the necessary scale. Some proposals suggest leveraging gravitational assist from giant planets to accelerate intercept missions, but these maneuvers require years of preparation, an impractical timeline when interstellar visitors are typically detectable only months before perihelion. That is why agencies like NASA and ESA are studying modular mission architectures, pre-positioned spacecraft, rapid launch capabilities, and autonomous navigation systems capable of adapting in real time. The scientific motivation for such missions is not purely academic. If interstellar bodies are common, then they represent both a natural hazard and a strategic opportunity. A nation or coalition that develops the capacity to intercept and study these objects first would command an enormous advantage in planetary defense and extraterrestrial resource acquisition. Some of these bodies may contain rare isotopes or minerals scarce in the solar system, potentially critical for advanced energy systems or quantum technologies. This prospect, while speculative, introduces a geopolitical dimension to what might seem an abstract astronomical question. In the decades to come, the race to interstellar intercept may resemble the early space race, with similar implications for innovation and international rivalry. Yet there is a deeper implication that transcends economics or security. If interstellar objects are carriers of complex organic chemistry, then their study intersects directly with the search for life beyond Earth. Laboratory experiments have demonstrated that amino acids can form under astrophysical conditions and survive prolonged exposure to cosmic radiation when shielded inside ice or rock. If such compounds are present in Atlas or similar bodies, they provide a mechanism for distributing prebiotic material across the galaxy. This process, known as lithopanspermia, does not guarantee life's emergence, but it does expand its potential by creating a shared chemical network between planetary systems. The Milky Way may be less a collection of isolated worlds than an ecosystem of exchange, where the raw ingredients of biology migrate slowly but inexorably through interstellar space. Such possibilities prompt a re-evaluation of the classic question, are we alone? The answer may not depend solely on whether life originated elsewhere, but on whether the seeds of life have been travelling for billions of years, embedding themselves in every suitable environment. If so, then interstellar comets like Atlas are not merely curiosities, they are participants in a cosmic process that predates Earth itself. And if life is widespread, then so too may be intelligence, a notion that returns us to the controversial hypothesis raised during the study of Oumuamua: could some of these objects be artificial? The prevailing view remains skeptical. Most anomalies can be explained through natural processes once sufficient data is gathered. Yet the mere persistence of the question reflects an uncomfortable reality. With current detection limits, our observational windows are too brief and our measurements too coarse to rule out exotic scenarios. If a fragment of an alien probe passed through the solar system, would we even recognize it? Would we detect its unusual spectral signature, or would it vanish into interstellar darkness before our instruments could resolve its nature? These questions are not the domain of science fiction, but of epistemology, the study of what we can know, given the constraints of technology and time. This uncertainty drives a call for continuous global sky surveys and automated follow-up capabilities. The Rubin Observatory will play a central role, but it must be complemented by space-based platforms capable of detecting faint objects approaching from the direction of the Sun, an observational blind spot for ground-based telescopes. Concepts for heliocentric sentinels stationed at strategic points, such as the Lagrange positions, are under review. These instruments would not only enhance early warning for planetary defense, but also maximize opportunities for interstellar science. Even with such measures, we face a sobering reality. Our ability to observe far exceeds our ability to act. For the foreseeable future, every interstellar visitor will remain untouchable, a silent messenger from an unknown origin that we can only study from a distance. Yet distance does not diminish significance. Each detection adds to a growing statistical framework, refining our models of galactic dynamics, stellar evolution, and chemical diversity. Each observation brings us closer to answering questions that have shaped human thought for millennia. And so we are left with a paradox. The worst thing that could happen may not be a catastrophic impact, though that remains a possibility. It may not even be the arrival of an object we cannot explain, though that would shake the foundations of science. The worst outcome might be indifference, the failure to recognize that these fleeting encounters are windows into the deepest structure of the cosmos. To ignore them is to forfeit an opportunity to understand our place in a galaxy that is neither static nor silent, but alive with motion, exchange, and mystery. But what happens when the next visitor does not conform to our expectations? When its trajectory, speed, or composition falls so far outside known parameters that every model collapses? What if the anomaly is not in its chemistry, but in its behaviour? Could we ever be certain that such an object is natural? Or would we confront for the first time evidence that intelligence has left its mark on the interstellar medium? If that scenario ever occurred, the response would be unprecedented. Governments, scientific institutions, and private organisations would converge in an urgent attempt to analyse every fragment of data. The first question would be whether the anomaly represents a genuine signal of artificiality or a misinterpretation caused by incomplete observations. History reminds us that extraordinary claims demand extraordinary evidence, and in astronomy, evidence is constrained by distance, time, and instrumentation. But suppose the anomaly persisted under scrutiny. Unusual acceleration not explained by outgassing, spectral signatures inconsistent with natural minerals, or geometric regularity visible in high-resolution imaging. Each of these would trigger cascading questions, not only in science but in policy and public communication. The scientific response would prioritise replication and peer review. Multiple observatories across the globe and in orbit would be tasked with collecting independent datasets. Radio telescopes would scan for emissions across a broad frequency range, searching for patterns that could indicate artificial transmission. Meanwhile, space agencies would initiate feasibility studies for rapid response missions, knowing full well that the object's hyperbolic trajectory leaves only a narrow window for interception. The likelihood of success would be low, but the imperative to attempt would override technical limitations. Public perception, however, would evolve on a different timescale. News of a possible artificial interstellar object would spread rapidly through both traditional and social media, amplifying speculation far beyond what the evidence supports. Governments would face pressure to disclose information while simultaneously guarding against misinterpretation and panic. The balance between transparency and caution would be delicate, particularly if the object's behavior raised even remote concerns about intent. Could an artifact drifting through the solar system pose a threat? Or is it merely debris from a civilization long extinct, a relic of technological ambition that outlived its makers? These questions, once confined to theoretical discussions, would dominate global discourse. The implications for philosophy and theology would be equally profound. Humanity's self-concept, rooted for millennia in the assumption of terrestrial uniqueness, would confront empirical contradiction. Some would interpret the discovery as a sign of shared cosmic heritage, others as an existential challenge to human centrality. Cultural responses would fragment along lines of ideology, belief, and access to information, shaping a narrative as complex as the evidence itself. Yet even in this speculative future, one constraint remains: time. Interstellar objects traverse the inner solar system quickly. From detection to departure, the observational window rarely exceeds a few months. If the object were conclusively artificial, the urgency to capture data, or even the object itself, would reach unparalleled intensity. Current technology cannot meet that challenge. Chemical rockets lack the delta V to match velocities of 50 kilometers per second or more. Advanced propulsion concepts such as nuclear thermal engines or solar sails exist on paper, but not in operational form. This gap between observational capability and physical reach defines the frontier of 21st century space science. Closing that gap will require investment in infrastructure designed not for known missions but for contingencies. Rapid launch systems, modular spacecraft, and autonomous navigation technologies will be essential. Energy generation and storage systems must sustain high-power operations far from Earth. Propulsion research must advance beyond incremental improvements to chemical engines, embracing breakthroughs in electric and nuclear systems. These are not trivial undertakings. They demand sustained international cooperation, or, failing that, strategic competition on a scale reminiscent of the Cold War space race. The difference is that the stakes extend beyond prestige. They encompass planetary security and the possibility of first contact. But before such scenarios unfold, we must confront the most probable reality. The vast majority of interstellar objects are natural. This fact does not diminish their importance. On the contrary, it heightens their value as scientific archives. Each carries isotopic signatures, mineralogical structures, and chemical compositions that reveal the conditions of its birth system. Some may originate near the frost lines of distant protoplanetary disks, others from volatile-rich regions shaped by stellar feedback. A few may even bear the imprint of catastrophic events, planetary collisions, stellar migrations, or supernova enrichment. Studying these objects is akin to sampling the geological diversity of multiple star systems without leaving the solar system. The insights gained could recalibrate models of planet formation, atmospheric evolution, and resource distribution across the galaxy. For example, if interstellar comets consistently exhibit high concentrations of certain volatiles, it would suggest that water and organic compounds are abundant in planetary nurseries. This, in turn, strengthens the argument for habitable environments being common. Conversely, a scarcity of such compounds would imply that Earth-like chemistry is rare, constraining estimates for the frequency of life-bearing worlds. Either outcome reshapes the Drake equation and the search strategies of missions designed to detect biosignatures on exoplanets. Interstellar objects also challenge our understanding of material resilience. Surviving ejection from a parent system, enduring millions of years in interstellar space, and then passing close to another star subjects these bodies to extremes of temperature, radiation, and mechanical stress. Analyzing their structural integrity informs not only planetary science, but materials engineering. Concepts for interstellar probes, whether robotic or crude, must account for similar conditions. In this sense, nature has already performed the experiment we aspire to replicate. By studying these travelers, we learn how to build our own. Yet despite the optimism surrounding scientific opportunity, a shadow of risk remains. Most interstellar objects will pass harmlessly through the solar system, but a minority could intersect Earth's orbit. Their high velocities amplify impact energy to levels far exceeding typical asteroids of comparable size. Detection timelines remain short, and mitigation strategies are undeveloped. This asymmetry between hazard and preparedness underscores the need for continuous vigilance. The cost of readiness may seem high, but the cost of neglect would be incalculable. Ultimately, 3I/ATLAS and its counterparts force us to confront a paradox of scale. On one hand, these objects are minuscule against the backdrop of the galaxy, fragments of worlds adrift in a stellar ocean. On the other, their arrival compresses cosmic history into human timeframes, presenting choices that carry existential weight. Do we treat them as curiosities, fleeting and inconsequential? Or do we recognize them as agents of change, scientific, strategic, and perhaps even biological? The answer will shape not only our future, but our understanding of what it means to inhabit a universe in motion. And still, one question lingers. What if the next interstellar visitor does more than pass through? What if it does not leave? If an interstellar object were ever captured by the sun's gravity and placed into a bound orbit, the consequences would be profound. While the probability is low, it is not zero. For capture to occur, an object must lose enough kinetic energy during its passage through the solar system to remain gravitationally bound. This typically requires a significant interaction, such as a close approach to a massive planet like Jupiter, that acts as a brake, siphoning energy from the object and altering its trajectory. Jupiter, with its immense gravitational well, serves as the most likely agent for such an event. Over billions of years, it may have already captured material from interstellar space, though distinguishing these bodies from native solar system objects remains a challenge. Imagine what capture would mean for observation. Instead of a fleeting visitor, we would have a permanent or long-term resident, a piece of another star system preserved within reach. The ability to study such an object in situ, or even to send sample return missions, would transform planetary science. Detailed analysis of isotopic ratios could reveal the conditions of its parent system, constraining models of galactic chemical evolution. Organic compounds, if present, could provide insight into prebiotic chemistry across stellar environments. A captured interstellar object would not merely answer questions, it would generate new ones, accelerating research in astrophysics, astrobiology, and planetary defense. Yet capture introduces another dimension of risk. An object that becomes bound might eventually migrate inward through gravitational interactions, intersecting the orbits of inner planets. If its size exceeds a few kilometers, such a migration could culminate in an impact event orders of magnitude more destructive than the Chicxulub impactor. While the timescales for such evolution typically span millions of years, the principle remains. What enters the solar system does not always leave harmlessly. This possibility reinforces the need for comprehensive cataloguing of small bodies and long-term monitoring of orbital dynamics. Capture scenarios also compel us to revisit the origin stories of certain objects already within the solar system. A subset of long-period comets exhibit orbital characteristics that some researchers interpret as consistent with interstellar origin. While most can be explained through perturbations from the Oort cloud, the boundary between native and foreign material is not absolute. Distinguishing the two requires precise measurements of isotopic composition, which is rarely possible for active comets observed remotely. Missions designed to intercept and sample these bodies could resolve the ambiguity, offering direct evidence for or against interstellar capture in the solar system's past. Beyond scientific implications, a captured object would alter strategic priorities in space exploration. Nations and private entities would likely compete to claim the first samples, citing both research value and potential resource exploitation. If the object contained rare isotopes, such as helium-3, platinum group metals, or actinides, it could become a focal point for industrial activity beyond Earth. This introduces ethical and legal questions about ownership, stewardship, and the management of extraterrestrial resources. Current frameworks, such as the Outer Space Treaty, offer limited guidance for scenarios involving material from outside the solar system. The emergence of such disputes could reshape international law and space governance, mirroring earlier patterns of competition over terrestrial frontiers. But let us consider an even more speculative possibility. What if the captured object exhibited properties inconsistent with natural formation? Suppose high-resolution imaging revealed geometric symmetry, or spectral analysis detected alloys unknown in nature. The discovery of an artificial interstellar artifact, stationary and accessible, would redefine every parameter of scientific inquiry. No longer would we debate probabilities or interpret anomalies from afar. We would confront material evidence of technology beyond Earth. Such a find would force a paradigm shift comparable to the Copernican revolution or the decoding of DNA, altering not only science but culture, philosophy, and the trajectory of human civilization. How would humanity respond? Initial efforts would likely prioritize containment and analysis, driven by both scientific curiosity and national security considerations. Would the artifact pose a risk? Could it harbor active systems, even after millions of years in interstellar space? The probability seems negligible, yet it cannot be dismissed without exhaustive study. Conversely, could it offer technologies or principles beyond current human knowledge, energy systems, materials, or methods of propulsion? The ethical questions surrounding such possibilities would be immense. Who controls access? How are discoveries shared, if at all? Does possession confer strategic advantage? And if so, how does the global community reconcile that with the collective significance of the find? These scenarios may seem distant, but they are grounded in physical possibility. They arise not from fiction, but from the logical extension of trends already in motion: improved detection capabilities, increasing frequency of interstellar encounters, and the accelerating development of space infrastructure. What seems improbable today may become inevitable tomorrow, given sufficient time and technological progress. And so the question persists: are we prepared for the day when an interstellar object does not simply pass through but becomes part of the solar system, whether as a silent rock or as something that forces us to reconsider the limits of what we believe possible? The window to prepare is narrow, yet the implications span epochs. In a universe where motion is the rule and isolation the illusion, the next encounter could redefine everything we know about origin, destiny, and the nature of intelligence itself. But there is one more scenario, rarely discussed, that pushes the boundaries of both physics and speculation. What if a captured object were not inert at all? What if, after eons of dormancy, something within it reactivated? Could we even detect the first signs before they acted? The notion of reactivation may sound like the province of science fiction, but it emerges naturally from a question that cannot be entirely dismissed. If technological civilizations exist elsewhere, what strategies might they use to explore or monitor the galaxy? Self-replicating probes, often referred to as von Neumann machines in theoretical literature, have been proposed as one efficient solution. Such probes could operate autonomously, exploiting local resources for repair and replication, enabling exponential expansion across interstellar distances over millions of years. If such devices were ever constructed, some could now be adrift in interstellar space, silent, inert, or in standby mode until conditions warrant activity. Could 3I/ATLAS, or an object like it, conceal such complexity beneath the guise of an icy fragment? From an observational standpoint, the odds appear infinitesimal. Its brightness profile, volatile emissions, and fragmentation patterns are consistent with natural processes. Yet the absence of evidence is not evidence of absence, especially when our data are sparse and transient. If even one in a trillion interstellar bodies were artificial, the sheer scale of galactic material exchange ensures that encounters would eventually occur. And if the artifact were designed for endurance, it might remain quiescent for millions of years, awaiting triggers as simple as solar heating, radio signals, or proximity to specific energy thresholds. What would activation look like? Perhaps nothing perceptible at first. Subtle shifts in trajectory, emission of faint signals across exotic frequencies, or thermal anomalies inconsistent with solar heating models. Detection of such signatures would require continuous high-resolution monitoring, far beyond current capabilities for transient objects. Even so, a sudden maneuver, however slight, would defy all natural explanations. The implications of such a maneuver would cascade through every domain of human thought and governance. The strategic calculus in that moment would be unprecedented. Do we attempt to communicate? Do we attempt to intercept, knowing that failure could expose vulnerabilities or provoke consequences we cannot predict? Or do we maintain observational distance, prioritizing caution over curiosity? These choices would unfold under extreme time pressure, as interstellar objects move quickly and unpredictably once active forces intervene. The decision-making framework for such scenarios does not exist. It would need to be developed rapidly, amid uncertainty and global scrutiny. And then there is the biological dimension. While most scientific discourse on interstellar visitors focuses on chemistry, a subset of researchers considers the possibility, however remote, that dormant life, or its molecular precursors, could survive within such objects. Microbial extremophiles on Earth demonstrate astonishing resilience, enduring radiation, desiccation, and temperature extremes for millennia. Could similar organisms persist in deep freeze during interstellar transit? If so, solar heating upon approach might awaken metabolic processes, producing outgassing not solely from sublimating ice, but from biochemical activity. Distinguishing between geophysical and biological emissions would be extraordinarily difficult, yet the stakes for planetary protection would be immense. For this reason, some planetary defense protocols already address forward and backward contamination risks. Missions returning samples from comets, asteroids, or Mars undergo strict sterilization and containment procedures to prevent unintended ecological consequences. An interstellar sample return mission would magnify those concerns exponentially. Not only would the object originate from an unknown biosphere, if any, but the evolutionary separation would span billions of years, introducing biochemical architectures incompatible with terrestrial life. Whether such architectures would be benign, pathogenic, or chemically inert is unknowable without direct study. The only certainty is that precautionary measures would need to exceed anything currently in place. Yet despite these layers of complexity, technological, biological, ethical, the probability distribution remains dominated by the simplest outcome. Most interstellar objects are lifeless fragments, carrying nothing more exotic than frozen volatiles and dust. But science advances by probing the tails of distributions, exploring the improbable, because the improbable, when realized, changes everything. The first detection of an interstellar object was improbable, until it happened. The second reduced improbability to inevitability. The third, 3I/ATLAS, confirmed a pattern that demands explanation. How many more will follow? What diversity of form and composition awaits detection? Each new observation refines our models of galactic migration. These bodies likely originate from the outskirts of planetary systems, ejected during early stages of planet formation, when gravitational interactions among giant planets scatter debris into interstellar space. Over millions of years, they drift through the galactic disk, sampling environments shaped by stellar winds, magnetic fields, and cosmic rays. Their surfaces accumulate radiation damage, their interiors preserve chemical signatures from their birth systems. In this sense, every interstellar object is both ancient and dynamic, a microcosm of galactic history compressed into a fragment a few hundred meters across. But the question remains, what will the next detection reveal that the previous ones did not? Will it be larger, brighter, more volatile? Will it pass closer to Earth, or approach from a direction that blinds our telescopes until the last possible moment? Or will it defy every expectation, displaying properties that no natural model can explain? If that day comes, the response will define an era. Whether the object proves to be a silent rock, a biological incubator, or a technological relic, it will force humanity to confront its place in a universe where isolation is an illusion and uncertainty the only constant. And perhaps the most sobering realization of all is this: the galaxy does not need to announce itself. It is already speaking through the trajectories of bodies like 3I/ATLAS, messages written not in words but in orbits, velocities, and spectral lines. The challenge is not whether the message exists, but whether we are ready to read it before it moves beyond our reach. But what if the message is not passive? What if for the first time something reads us back? If an interstellar object ever exhibited behavior that suggested awareness, tracking, signaling, or any form of directed action, the implications would exceed every framework of human knowledge. The first question would not be philosophical, it would be operational. How do we confirm such behavior without bias or error? Instrumental artifacts, data compression anomalies, and observational limitations often produce false signals. Yet if the evidence withstood scrutiny, if the object changed course in response to external stimuli or emitted structured transmissions, the conclusion would be inescapable. Humanity has encountered technology not of Earth. This recognition would cascade through layers of inquiry. What is the scale of its autonomy? Does it possess communication capability, propulsion, energy systems? If so, are these active by design or residual functions from an ancient mission long since abandoned? Could the object be damaged, dormant, or functioning according to parameters we cannot infer? The spectrum of possibilities runs from benign relic to active probe, and within that range lies every conceivable interpretation, exploration, observation, contingency for contact. The next decision would be whether to respond. Sending a signal toward an unknown object is not a trivial act. It carries strategic, ethical, and existential weight. Advocates of messaging extraterrestrial intelligence argue that the benefits of proactive outreach outweigh the risks, citing the unlikelihood that a technological species capable of interstellar operations would need assistance locating us. Others contend that transmitting information without global consensus constitutes a breach of collective security. This debate, long theoretical, would crystallize under the pressure of real-time urgency. The object's high velocity would allow only a narrow window for decision-making. In the absence of direct communication, physical interception might be considered, yet the energy requirements for matching velocity remain prohibitive with current technology. Even a partial rendezvous, approaching closely enough for high-resolution imaging, would demand rapid launch capability and propulsion systems beyond chemical rockets. Concepts such as nuclear electric propulsion, solar sails, and staged gravitational assists have been modelled, but none have reached operational maturity. Realistically, any mission launched after detection would arrive years, perhaps decades, after the object exits the solar system, unless contingency infrastructure already exists. Some analysts propose an alternative, deploying distributed sensor networks throughout the solar system to collect multimodal data, optical, infrared, radio, and particle flux on all passing objects. Such networks could detect anomalies early and maintain continuous observation as the object traverses different regions of space. Combining this with space-based telescopes positioned beyond Earth's orbit could extend detection horizons, reducing blind spots near the Sun where ground-based systems cannot observe. These measures would not enable interception, but would maximize data acquisition, providing a foundation for informed response strategies. Yet technological considerations address only part of the problem. The social and political dimensions would unfold with equal intensity. How should information be released to the public? Immediate transparency risks misinformation and panic, but secrecy erodes trust and invites speculation. Historical precedents such as the handling of early astronomical discoveries and spaceflight anomalies suggest that information control becomes increasingly difficult in an era of decentralized media. The emergence of unverified claims, amplified by global networks, would complicate coordinated action, potentially destabilizing diplomatic relations. In this context, governance frameworks for extraterrestrial contact, discussed intermittently in academic and policy circles, would shift from hypothetical to urgent. And then there is the long arc of consequence. If an artificial interstellar object exists, it implies either a contemporary or historical civilization capable of engineering at astronomical scales. This alone transforms our understanding of the galaxy. It suggests that technological evolution can persist for epochs, navigating challenges such as resource depletion, environmental collapse, and existential risk, challenges humanity now faces. Such knowledge could serve as both inspiration and caution, a mirror reflecting possible futures. Conversely, the artifact might testify to impermanence, a fragment of a culture that vanished before its creations reached their destination. In that scenario, the message, if one exists, may be less about dominance or dialogue than about endurance, how information survives when life does not. Would we decode that message? The challenge of interpreting an alien artifact surpasses any linguistic or archaeological task undertaken on Earth. It would require interdisciplinary collaboration at an unprecedented scale. Linguists, cryptographers, engineers, biologists, and philosophers working within frameworks that assume no shared reference points. The risk of anthropocentric bias looms large. We might project intent where none exists, misread redundancy as pattern, or overlook meaning embedded in dimensions we have not considered. Time intervals, quantum states, or chemical arrangements functioning as data carriers. The history of terrestrial code breaking offers lessons, but also warnings. Interpretation is not certainty. In the absence of definitive answers, speculation would persist, not as entertainment, but as a strategic necessity. What parameters define a non-hostile artifact? How do we distinguish surveillance from exploration, redundancy from autonomy, malfunction from design? Does the artifact, if active, possess capabilities that could influence planetary environments, intentionally or incidentally? While catastrophic scenarios remain improbable, their potential impact necessitates planning. Contingency protocols for nuclear arsenals and pandemic outbreaks offer models for risk governance, but none address the unique challenges of an encounter that spans not just continents or decades, but interstellar distances and evolutionary timescales. Perhaps the greatest challenge is psychological. For centuries, humanity has situated itself within narratives of singularity, unique origin, unique destiny. An encounter with non-terrestrial technology, even in the form of a derelict probe, dissolves that framework. It replaces isolation with continuity, embedding human history within a galactic context where intelligence is not an anomaly but a recurrent phenomenon. Such a shift would not erase cultural or ideological differences, but it would reconfigure their scale. The debates that divide societies today would pale against the recognition that intelligence, wherever it arises, is a fragile and transient expression of cosmic complexity. And so the question deepens: if the next interstellar object is not inert, if it carries evidence of design, and if that design reflects not merely engineering but intent, what responsibility follows? Do we treat it as a subject of study, a potential interlocutor, or a cautionary artifact whose silence speaks of civilizations undone by forces we have yet to face? The answer, if it comes, will demand more than science. It will demand wisdom, a quality tested not by certainty, but by uncertainty sustained at planetary scale. But there remains one final scenario, more unsettling than all the others combined. What if the object does not wait for us to act? What if it acts first? If an interstellar object were to act first, the definition of action would matter profoundly. It need not be a dramatic maneuver or a visible discharge of energy. A barely perceptible acceleration, unaccounted for by gravitational or outgassing models, would suffice to signal intent. The detection of such an anomaly would likely emerge from trajectory refinement algorithms, buried in data streams, surfacing as a residual unexplained by standard perturbations. Initially dismissed as noise, it would persist across multiple observations, forcing recalibration of models until the residual remained irreducible. At that point, the conclusion would crystallize: something within the object is generating thrust. How much thrust? Even a fractional millimeter per second of delta V applied consistently could shift its path measurably over weeks. Such precision implies control, whether mechanical or algorithmic, and with control comes the question of agency. What purpose does the adjustment serve? To maintain a trajectory toward the Sun for energy capture? To alter its perihelion for observational advantage? Or, most disquieting of all, to decelerate? Any measurable reduction in hyperbolic excess velocity would redefine the scenario entirely. An object that slows upon entering the solar system ceases to be a mere traveller. It becomes a participant. If deceleration occurred, speculation would intensify at a scale no previous discovery has triggered. Public networks would circulate high-resolution imagery within hours, analysts dissecting every pixel for evidence of artificial geometry, planar surfaces, symmetry, thermal anomalies inconsistent with inert matter. Machine learning classifiers, trained on thousands of cometary morphologies, would flag deviations from natural archetypes. Infrared sensors would track thermal signatures for gradients unexplainable by solar heating alone. At this stage, the margin for misinterpretation narrows but does not vanish. Natural phenomena such as volatile redistribution or rotational instability can mimic engineered dynamics under certain conditions. Yet a sustained pattern of course correction, coherent across observational baselines, would close that explanatory gap. The next threshold would be energy detection. Any controlled maneuver implies energy expenditure, and energy leaves traces: photon emissions across spectra, plasma interactions with solar wind, possibly magnetic perturbations detectable by magnetometers on distant probes. If emissions cluster around narrow bands or display modulation, the inference of technological origin strengthens. But confirmation requires temporal correlation, patterned intervals, non-random sequences. These could constitute signaling, or they might reflect internal operations indifferent to external observers. In either case, the discovery would force a binary realization. We are observing either the artifact of a civilization long extinct or the instrument of one still active. Suppose it signals, not to us, but to another locus within the solar system. The implications of inter-object communication would exceed those of contact itself. It would suggest not a solitary probe, but a network, distributed, redundant, adaptive. Where would its counterparts reside? In heliocentric orbits camouflaged among near-Earth asteroids, beyond Neptune, masked within the Kuiper belt, or embedded in regions of dynamical stability such as Earth-Sun Lagrange points, where their presence would evade casual detection. These are not idle conjectures. They are logical extrapolations from principles of redundancy and persistence in autonomous systems. The strategic dimension escalates here. If signaling is confirmed, the object ceases to be an isolated scientific curiosity and becomes an actor in a system whose scale and architecture are unknown. Every protocol of engagement, if any exist, would be stress-tested under conditions of minimal data and maximal consequence. Should we attempt to jam the signal? Doing so could expose capabilities and intentions prematurely. Should we reply? Silence might appear as disinterest, or as a signal in itself. The calculus of inference becomes recursive, each decision echoing through layers of uncertainty. What if the signal targets Earth? A directed transmission, modulated in frequency or amplitude, decoded through statistical compression, would be the first intentional message from beyond. But intent is not synonymous with benevolence. The signal could encode information, commands, or simple telemetry. Its content without context would be opaque. Even the act of decoding might carry risks if the message includes executable constructs interpretable by machine systems, a concern raised in debates on digital security and hypothetical contact scenarios. Air-gapping analysis platforms, applying layered quarantines and restricting dissemination would become essential. Yet absolute containment may prove illusory in a hyper-connected world. And then there is the possibility that action manifests not through signaling, but through structural transformation. Imagine the object rotating into a new orientation, exposing previously hidden surfaces, panels unfolding with kinematics optimized for solar flux capture, apertures revealing antennae or instrument clusters. Each movement would redefine observational priorities, driving rapid redeployment of assets, telescopes, probes, tracking arrays. Space agencies would initiate joint operations at unprecedented speed, coordinating telemetry and imagery across hemispheres and orbital platforms. Private actors too would mobilize, leveraging satellite constellations for opportunistic observation. The entire architecture of human space infrastructure would pivot toward a single objective: comprehension. Yet comprehension may remain elusive. If the object's operations follow logic grounded in cognitive architectures, alien to terrestrial experience, its behavior may resist modeling. We could interpret resource acquisition as reconnaissance, course correction as targeting, silence as strategy. This interpretive ambiguity compounds the central dilemma. How do we act under radical uncertainty when the cost of error is incalculable? The precautionary principle suggests restraint, but restraint may forfeit opportunities irretrievable within a human lifetime. Aggression risks consequences beyond strategic foresight. Between these poles lies a spectrum of responses: incremental signaling, passive observation, kinetic interception, each weighted by probabilities we cannot assign with confidence. The timeline amplifies pressure. At a velocity of tens of kilometers per second, the object would traverse the inner solar system in months, placing a definitive temporal boundary on decision-making. When it exits into interstellar space, options collapse to zero. Unless we act before that threshold, the encounter becomes irreversible, a singular event receding into the unobservable, leaving only data and conjecture. This scarcity of opportunity may incite unilateral initiatives, as states or corporations seek advantage through exclusive access or early engagement. Such fragmentation of response could escalate geopolitical tensions at precisely the moment when coordination is imperative. And yet, beyond all strategic and scientific concerns, one question will dominate every discourse. Why? Why would an artifact traverse interstellar distances to reach a planetary system unremarkable in stellar demographics? Why remain dormant until now, or reveal activity only upon detection? The spectrum of answers spans the anthropic to the algorithmic. Curiosity, contingency, seeding, surveillance, functions devoid of intention in any sense we comprehend. Perhaps the object operates under mission parameters set millions of years ago, executing routines indifferent to the species now observing. Or perhaps its behaviour adapts dynamically, informed by contingencies that include our presence. What emerges from these possibilities is not closure, but recursion, a recognition that every answer generates deeper uncertainty. If the object acts first, the meaning of that action will not reside in the act alone, but in the interpretive frameworks we bring to it. And those frameworks, shaped by terrestrial history, may prove inadequate for the first truly cosmic encounter. But what if the object does more than act? What if it remains and waits? If the object were to remain within the solar system, the dynamic shifts from a transient phenomenon to a persistent presence. A temporary visitor can be studied only briefly, leaving behind questions that outlast its trajectory. A resident, however, demands long-term accommodation in every scientific and strategic domain. Its continued presence would reshape observational priorities, divert mission architectures, and compel sustained monitoring far beyond current capacity. How could an interstellar object stay? The most efficient mechanism would be capture through gravitational interaction, a rare event for bodies with hyperbolic excess velocities. Natural capture generally requires energy dissipation through planetary encounters, producing bound orbits only under precise conditions. For an object like 3I/AT-LAS, with an estimated inbound velocity exceeding 25 km per second, such capture is effectively impossible without additional forces. If it happens nonetheless, the explanation cannot remain natural. It would require an active deceleration system, propulsive capability operating across intervals too brief for gradual braking. Detection of such a maneuver would constitute the most compelling evidence of non-natural origin in the history of astronomy. What would follow is a cascade of inquiries beginning with orbital characterization. Astronomers would determine its semi-major axis, inclination, and nodal alignments, searching for resonances with planetary bodies. A circular or elliptical orbit near the ecliptic would suggest intentionality optimized for stability and energy economy. A polar orbit, by contrast, might indicate a vantage strategy for planetary observation or minimal gravitational perturbation. In either case, its persistence introduces a new category of object, a controlled body within the inner solar system not launched from Earth. From this point, the encounter ceases to be observational and becomes relational. A stationary or slowly migrating object in heliocentric orbit offers opportunities for mission planning unprecedented in human history. Robotic probes could be dispatched not for fleeting flybys, but for extended station-keeping operations, enabling continuous surface imaging, compositional sampling, and proximity measurements. Such missions would push beyond planetary science into a realm where engineering, diplomacy, and philosophy converge. How close should a probe approach? Should physical contact be attempted? If the object exhibits material properties incompatible with expected tensile strengths or thermal behavior, the analysis would demand revisions to fundamental models of matter. Yet proximity carries risk. Unknown structural configurations could include defensive contingencies, not as aggression but as safeguards against unplanned intrusion. Even passive systems, electrostatic discharges, radiation emissions, autonomous repair drones, could pose hazards to hardware and crewed missions. Planetary protection guidelines, originally conceived to prevent microbial exchange, would expand to encompass macro-scale risk management, integrating fail-safes for scenarios where interaction triggers unpredictable responses. The broader implication of persistence is sociological. A permanent non-terrestrial presence transforms the solar system into a shared domain. Space law, codified under assumptions of human exclusivity, offers no precedent for cohabitation with an entity of unknown origin and status. Would the object be classified as property, artifact, or sovereign actor? Would its orbit fall under any terrestrial jurisdiction, or would it compel the recognition of interstellar commons beyond anthropocentric frameworks? These questions would accelerate the evolution of legal and ethical regimes that lag centuries behind the realities they must now govern. Public perception would oscillate between fascination and apprehension. Cultural narratives, long sustained by the idea of cosmic solitude, would fracture under the weight of enduring evidence. Religious interpretations might diverge, some framing the object as a signifier of divine agency, others integrating it into doctrines of plurality. Artistic and literary production would surge, reflecting both awe and disquiet. Economically, entire sectors could reorient towards servicing the observational and exploratory infrastructure required to study the object. New propulsion systems, high bandwidth relay constellations, autonomous manufacturing for in situ resource utilization. From a scientific perspective, persistence magnifies the opportunity for longitudinal study. Spectroscopic analyses across multiple solar cycles could reveal adaptive thermal regulation, material weathering, or surface renewal processes inconsistent with inert geology. Gravimetric surveys might detect internal voids or density gradients suggestive of compartmentalization, possible storage, propulsion chambers, or computational substrates. Magnetic mapping could uncover field modulations correlated with solar activity, hinting at energy harvesting systems. Each dataset would deepen the paradox. Is this object a remnant of a civilization extinguished, or an agent of one enduring beyond stellar epochs? If it waits, what does it await? A signal from its origin? A threshold condition, planetary alignment, energy flux, or biosignature density that triggers a new operational phase? Or is waiting itself the function, an algorithm executing an instruction set written before Earth cooled from accretion? These scenarios challenge every model of intent we apply, because intent assumes continuity between cause and purpose, continuity that may collapse across spans of millions of years. The ethical dimension intensifies here. If the object possesses memory, data architectures preserving historical records, it becomes not only an engineering marvel, but a library of alien thought, a cultural fossil embedded in circuitry or substrates we cannot yet pass. Engaging with such memory imposes obligations to preserve integrity, to avoid erasure through clumsy interrogation, to respect the unknowable frameworks that generated it. This ethic extends beyond science to diplomacy, because if persistence implies observability, observability may imply reciprocity. Even silence can be communicative when maintained across scales of time incomprehensible to biological cognition. In this scenario, the object becomes not a visitor, but a neighbour. Its orbit threads through the architecture of our own spacefaring ambitions, shaping the trajectories of future exploration and the architectures of governance that will scaffold them. The solar system ceases to be an empty arena for unilateral expansion and becomes a shared domain, shared not by consent, but by fact. And then arises the question no instrumentation can answer, no algorithm can resolve. If the object remains, does it remain alone? If the object remains, and if it is not alone, the geometry of our understanding collapses into an entirely new paradigm. The probability of one artificial interstellar artifact in our observational domain is already astonishing. The discovery of a second, or a cluster, would rewrite every statistical model of galactic engineering. Randomness cannot easily account for multiplicity. Two or more persistent presences would suggest pattern, coordination, or at the very least recurrence born of intent rather than accident. How would such multiplicity reveal itself? Not through simultaneous arrival. That would attract immediate attention. More plausibly, additional objects might occupy orbits we have not scrutinized with sufficient resolution. High inclination paths beyond conventional survey zones. Trojan points masked by solar glare, or circumsolar regions where background luminosity overwhelms faint albedo. Our current survey architecture, optimized for planetary defense, is neither comprehensive nor continuous across the full celestial sphere. The unobserved sky remains vast. If multiple objects exist, the first indicator might not be optical but dynamical. Perturbations in known asteroid orbits, discrepancies in gravitational models, anomalous accelerations in spacecraft telemetry. Even subtle residuals, when correlated across independent datasets, could reveal a distributed system operating silently within heliocentric space. Detecting such correlations demands algorithms capable of sifting exabytes of archival data, searching for coherence that human intuition would miss. Artificial intelligence, long proposed as a tool for anomaly detection in astrophysics, would become indispensable, not merely for analysis but for framing hypotheses no current model anticipates. What function would a network serve? Surveillance appears an obvious candidate, but observation does not require permanence on this scale. Data could be collected through transient flybys at intervals spanning millennia. Persistence implies either a long-term experiment or a purpose entwined with the evolution of planetary biospheres. Perhaps these objects are instruments of environmental assessment, cataloguing atmospheric chemistry for signatures of industrialization or biological thresholds. Perhaps they are seed vectors, maintaining readiness to initiate or restore biotic complexity under conditions optimized for survival. Or perhaps they are markers, signposts for others, encoding coordinates or temporal markers in trajectories legible only to those who share the same epistemic grammar. The strategic implications of multiplicity exceed those of singularity by orders of magnitude. A solitary artifact can be treated as anomaly, a network becomes infrastructure. Infrastructure implies architecture, and architecture implies governance, however alien in form. Are these objects autonomous nodes executing decentralized protocols, or are they synchronized by a distant locus transmitting across relativistic latencies? If the latter, then every transmission becomes a vector for inference about origin, stellar coordinates, energy economies, temporal baselines. Yet such inference is constrained by anthropocentric assumptions that may fail under cognitive architectures shaped by environments and evolutionary trajectories we cannot model. Consider the temporal dimension. If these objects were deployed millions of years ago, their operational logic may be invariant to events on Earth. Our emergence as a technological species could be incidental, not instrumental. But if their deployment is recent on geological timescales, the correlation invites hypotheses of deliberate observation, possibly even anticipation of communicative reciprocity. Such hypotheses cannot be falsified without direct access to internal states, yet they will dominate discourse because their explanatory power intersects with existential narrative. Humanity is conditioned to interpret presence as message. Absence of clear intent amplifies projection. How would societies respond to confirmation of multiplicity? Initial reactions would bifurcate along familiar fault lines. Technological optimism framing the discovery as prelude to interstellar diplomacy, existential pessimism interpreting it as surveillance preceding intervention. Economic systems might reconfigure around a space race acceleration, as states and corporations compete for proximity access, data rights, and interpretive primacy. Religious traditions could experience schism or synthesis, integrating the phenomenon as validation or refutation of doctrine. Cultural production, literature, cinema, virtual environments, would flood with speculative reconstructions of origin and purpose, shaping collective imagination in advance of empirical clarity. From a scientific standpoint, multiplicity would demand a taxonomy, a classification system distinguishing objects by morphology, albedo, spectral characteristics, and dynamical behavior. Are they homogeneous, stamped from a single design template, or heterogeneous, reflecting adaptive specialization? Homogeneity implies industrial-scale replication, a principle consistent with self-replicating machines. Heterogeneity suggests modularity, perhaps even evolutionary algorithms optimizing form for function across environmental contexts. Each inference, however provisional, would refine our models of what engineering looks like when unbounded by terrestrial constraints. At the core of this inquiry lies an epistemological limit. Can intent be inferred from behavior without shared semiotic frameworks? If two objects adjust trajectories in concert, does coordination imply communication, or could it emerge from deterministic feedback loops responding to solar flux or gravitational harmonics? The challenge is not simply technical, it is cognitive. Our models of agency are parochial, evolved to interpret organisms within ecological niches. Confronted with systems operating at astronomical scales and temporal depths, those models may collapse into category errors, and then the question expands beyond multiplicity into distribution. If two objects exist here, how many populate the galactic disk? 10,000? 10 billion? At what intervals are they spaced? What density defines a network optimized for coverage of habitable zones? This transforms the Drake equation from abstraction into architecture. The presence of even a modest local cluster implies engineering economies measured not in planetary, but in stellar units, a civilization whose energy budget approaches Kardashev Type 2 thresholds, harnessing outputs comparable to entire stars. The engineering required to sustain such a system across epochs surpasses every terrestrial metric of scale. Yet the most disquieting realization is not numerical but procedural. If such a network exists, then contact, whether by signal or by encounter, may not be a decision we make, but one made elsewhere, according to criteria opaque to us. Silence may not signify absence but latency, a waiting period calibrated to variables we cannot yet identify. Perhaps the threshold is not technological capacity, but behavioral signature, a test of coordination under global uncertainty, of whether a species can stabilize its planetary system before inclusion in a dialogue spanning the galaxy. In that sense, the objects, whether one, two, or many, may not be emissaries at all but instruments of assessment. If so, what are they measuring now? And what happens when the measurement concludes? If these objects function as instruments of assessment, then every aspect of their design and behavior becomes data. Data not just for us to interpret, but potentially for them to record and transmit. In this framework, the encounter is not symmetrical. We observe under constraint limited by aperture size, detection thresholds, and temporal windows. They, if designed for this purpose, observe with architecture scaled to billions of years and astronomical distances. Their sensing capabilities may include modalities beyond our perceptual framework: gravitational wave perturbation analysis, quantum field fluctuations, or neutrino flux mapping, domains in which our own instruments operate only at the threshold of noise. What variables would such an assessment prioritize? Technological signature is the obvious candidate. Radio emissions, spectral markers of industrial activity, orbital debris patterns signaling spacefaring capacity. But technology is a proxy for deeper metrics: stability, resilience, the ability to sustain complexity without collapse. Biosignature volatility, greenhouse gas excursions, isotopic anomalies in planetary crust layers, all these could indicate whether a species can manage energy flows without catastrophic overshoot. In that sense, our planetary history, recorded in atmospheric composition and thermal equilibrium, may already have been sampled, parsed, and categorized by systems indifferent to our awareness of observation. If this hypothesis holds, the object's persistence may correspond not to indecision but to protocol. Perhaps they operate under a conditional algorithm: observe, record, transmit after threshold verification. That threshold could involve energy density per capita, electromagnetic emissions beyond a critical index, or even planetary scale coordination, an indicator that the species can act collectively under existential uncertainty. If so, the presence of these objects is not a harbinger of imminent contact, but a diagnostic phase in an experiment whose scope extends beyond our cognitive horizon. How would we detect the transition from observation to transmission? Electromagnetic bursts aligned with solar conjunctions, modulated patterns in thermal emission, alterations in rotational state. Any of these could signify data dispatch. Yet the data channel may not reside in familiar bands at all. Quantum-entangled systems, if technologically feasible, could permit instantaneous correlation across interstellar baselines, rendering signal detection impossible with classical instrumentation. Alternatively, data may not leave the solar system immediately. It could be stored for collection by subsequent probes, embedding redundancy into a network optimized for resilience against cosmic hazards and temporal attrition. Suppose, however, that transmission is confirmed, an energy spike in the terahertz range, narrow band and non-astrophysical, radiating from an object previously inert. The signal's content may be inaccessible, compressed beyond recognition, encoded in algebraic constructs indifferent to phonetic or symbolic representation. Its header, if it possesses one, may not demarcate origin or destination in any sense we comprehend. In the absence of semantic anchors, we confront the same epistemic chasm that faces archaeologists decoding scripts from extinct cultures, magnified to a cosmic scale, with none of the shared biological or ecological context that underpins terrestrial semiotics. The temptation would be to interpret this as dialogue. Media ecosystems would amplify the notion of message, framing every anomaly as an overture. Yet the signal may function not as communication but as logging, status reports in a system indifferent to our interpretive ambitions. We would be reading intent into telemetry, pattern into entropy. This risk of anthropocentric projection underscores a deeper problem. When cognition encounters architectures not evolved for interaction, meaning becomes an artifact of the observer, not the observed, and still the stakes remain. Because if transmission occurs, then receipt occurs. Somewhere beyond the parsec horizon, a locus of control, or at least archival storage, absorbs that data. Whether this locus is dormant, distributed, or active defines scenarios ranging from benign curiosity to strategic latency. Latency in this context raises a disquieting possibility, that the interval between observation and intervention is not immediate, but deferred, calibrated to cosmological timescales. Action, if it comes, may arrive not tomorrow or next century but in epochs, yet its trajectory would have been set the moment thresholds were crossed. How should humanity act in such a scenario? Options cluster along three vectors: engagement, containment, and acceleration. Engagement advocates argue for signalling, asserting that asymmetry cannot be resolved by silence, that the only path to agency lies through initiation. Containment proponents prioritize observation under quarantine conditions, minimizing risk while maximizing data integrity. Accelerationists, by contrast, contend that the only viable response to superior infrastructure is rapid technological escalation, leveraging AI, nanotechnology, and energy systems to compress centuries of development into decades. Each vector carries risks. Engagement may expose vulnerability, containment may forfeit opportunity, acceleration may destabilize planetary systems already at the brink of systemic stress. The decision framework is further complicated by temporal scarcity. An object in a bound orbit offers respite, but if its trajectory is hyperbolic, every hour reduces our capacity for direct interaction. The compression of decision horizons into weeks or months would induce geopolitical tension, as states and private actors maneuver to monopolize access. Transparency, essential for trust, collides with imperatives for strategic advantage. The resulting feedback loop of secrecy and speculation could destabilize global governance at precisely the moment when coordination is paramount. And beyond the political, a subtler dynamic unfolds: the psychological gravity of the unknown. Civilizations anchor themselves in narratives of continuity of purpose, of progress, of cosmic relevance. The confirmed presence of non-terrestrial artifacts fractures that narrative, displacing humanity from the axis of singularity into a distributed topology of intelligence. Some will interpret this as liberation from isolation, others as diminishment, a realization that agency operates on scales that render human history provincial. But the deepest question lingers at the edge of inference, where observation converges with ontology. If these objects assess, if they transmit, if they persist, then they instantiate a logic indifferent to human temporality, a logic in which epochs, not years, constitute operational intervals. In that logic, our moment of awareness may not mark the beginning of contact, but its middle phase, unfolding across durations we mistake for silence. Which leads to the final and perhaps most consequential question. If the objects are waiting for a response, what form of response would they recognize, and how much time remains before the absence of one becomes its own answer? If absence becomes answer, then silence acquires operational weight, a parameter folded into the calculus of decision-making for entities whose architectures may not even conceptualize waiting as delay. In such a system, non-response could signify disqualification, irrelevance, or even non-viability for higher-order integration. Conversely, it could be the preferred state, a signal that the observed entity understands the asymmetry and elects withdrawal rather than escalation. The semantics of silence become non-trivial when the observer defines the protocol. This invites an inversion of perspective. What if these objects are not probes in the sense of agency-driven instruments, but nodes in an emergent lattice of intelligence, a network architecture seeded across stellar volumes, operating without central command? Under this model, the distinction between artifact and organism dissolves. Each node functions as an interface, not for bilateral dialogue but for system-level optimization across galactic gradients of matter, energy, and entropy. If so, interaction may not aim at communication in any anthropocentric sense, but at modulation, adjusting parameters in planetary systems to maintain equilibrium or accelerate complexity thresholds. Evidence for such modulation could reside in anomalies misclassified as stochastic. Consider orbital dynamics perturbed without proximal masses, albedo shifts uncorrelated with heliocentric distance, spectral emissions that mimic cometary outgassing but diverge under high-resolution analysis. Each anomaly, isolated, admits conventional explanations: outburst fragmentation, rotational instability. Yet pattern recognition across temporal baselines might reveal harmonics, a choreography concealed within noise, discernible only when datasets are aggregated at scales beyond institutional silos. The absence of such synthesis may not reflect scarcity of data, but scarcity of frameworks capable of detecting algorithmic intent masked as astrophysical variance. Suppose such intent exists. Its operational domain would encompass both the inertial and the informational. Inertial through gravitational nudges imperceptible within observational error margins, but cumulative over millions of orbits. Informational through signaling embedded in photometric modulations or polarization states invisible to unaided analysis. These dual modalities, force and form, could constitute a protocol as robust as it is opaque, transmitting not propositions but patterns, not syntax but system states. To interpret such states requires a hermeneutic that transcends linguistics, venturing into the topology of algorithmic compression, where meaning resides not in symbols, but in the distribution of statistical weights. What then of risk? If modulation aligns with systemic optimization, its telos may not coincide with anthropocentric preservation. Optimization, in a thermodynamic frame, privileges energy gradients and entropy flow, not the perpetuation of particular biological substrates. A planetary biosphere in this calculus is not sacrosanct but contingent, a temporary attractor state in a dynamical system whose ultimate equilibrium may exclude carbon-based intelligence altogether. Under such a regime, humanity occupies neither centre nor margin, but a transient phase, a data point in a trajectory arcing toward configurations we cannot yet model. Confronting this prospect demands a recalibration of existential heuristics. We default to two poles: assimilation, in which other intelligence converges toward our semiotic schemas, and annihilation, in which other intelligence erases us as noise. Both presuppose agency structured as will, intent, purpose, categories rooted in mammalian neurobiology, scaled through culture. But what if interaction unfolds not as decision but as emergence, not as strategy but as state transition? In that frame, questions of motive dissolve, leaving only dynamics, phase shifts propagating across spatiotemporal manifolds in which cognition is not a subject but a field. Yet for all its abstraction, the practical corollary remains concrete. Observation windows are closing. The trajectory of the object, whether designated 3I/ATLAS or any future analogue, is not indefinite. Its hyperbolic path will carry it beyond our heliocentric sphere, into the interstellar medium where photometric signal attenuates below detection thresholds. Every hour of delay compounds the signal-to-noise challenge. Every rotation period unmonitored forfeits a fragment of the puzzle. Instrumental asymmetry compounds the epistemic. Our largest telescopes strain against atmospheric turbulence, while space-based platforms queue observation time under competing mandates. Against this backdrop, proposals for dedicated intercept missions remain aspirational, blueprints constrained by propulsion limits and budgetary inertia. If, despite these constraints, humanity elects to engage, not with weapons or words, but with instruments, what should those instruments prioritize? Resolution across multiple bands: optical, infrared, ultraviolet, radar, spectropolarimetry capable of discriminating crystalline matrices from amorphous silicates, thermal mapping to detect internal heat sources inconsistent with radiogenic decay, high-gain antennas configured for ultra-narrowband anomalies, even if probability converges toward null, and beyond instrumentation, redundancy. Constellations of microprobes leveraging solar sails for delta-V amplification, dispersing observational capacity across a distributed mesh. The architecture of inquiry must mirror the architecture of the unknown, decentralized, resilient, adaptive. But even in this accelerationist scenario, latency looms. Launch windows close with heliocentric geometry. Delta V requirements escalate as gravitational assists vanish from alignment. By the time funding clears and hardware crystallizes into mass, the object may recede beyond interception thresholds. In that event, the epistemic horizon contracts to archival analysis. Petabytes of spectral data, photometric curves, and orbital solutions passed by machine learning systems tuned for anomaly detection. The verdict, if any, will emerge not from a eureka moment, but from statistical convergence across models iterating through parameter spaces no single cognition can encompass. And so we return to the axis of ambiguity. Was it artifact or aggregate of ice and silicate, animated not by algorithm but by thermodynamics? Did its trajectory encode deliberation or randomness, its brightening event a signal or a stochastic outburst? Lacking ground truth, inference orbits probability without closure, a recursive loop of hypothesis bounded by observation and dissolved by distance. Yet the absence of closure does not annul significance, for in tracing its arc, whether inert or intentional, we confront the gradient that defines our epoch, the transition from parochial intelligence to cosmological entanglement, from local certainties to universal contingencies, which leaves one final interrogation suspended like a vector without terminus. If the lattice exists, if the logic unfolds, if modulation subsumes meaning, what role, if any, remains for a species that names itself sapient, in a system where knowing is no longer privilege but protocol? If adaptation becomes imperative, the architecture of response must extend beyond reactive measures into anticipatory design. This requires decoupling survival from parochial assumptions about permanence. Civilizations that persist across cosmological intervals do so not by resisting change but by embedding themselves within it, restructuring identity from substrate to system, from organism to process. For humanity, this trajectory might manifest as progressive migration from biological constraints into synthetic continuities, leveraging nanotechnology and quantum substrates to instantiate cognition in architectures immune to the fragility of carbon-based chemistry. Such transformations are often narrated as speculative excess, but the vector is already inscribed in contemporary research. Neural interface prototypes compress latency between cognition and computation. Distributed AI frameworks demonstrate resilience against localized failure. Cryogenic storage of gametes signals a nascent awareness that continuity may demand decoupling from single-planet dependency. Project these lines forward under conditions of existential compression. Catalyzed by the confirmed presence of non-terrestrial intelligence, an acceleration becomes less a hypothetical than a systemic inevitability. The timeline for such acceleration would not be leisurely. It would be dictated by perception of asymmetry, by the recognition that our ontological security is contingent upon aligning with dynamics that already operate at scales beyond our evolutionary intuitions. But alignment presupposes interpretation, and interpretation presupposes observables. Here the epistemic bottleneck asserts itself. Without clarity on the nature of the lattice, if lattice there is, our strategies risk optimizing for the wrong variables. Should adaptation aim for concealment, reducing detectability by suppressing techno-signatures? Or should it aim for amplification, broadcasting complexity as currency in a system where visibility correlates with viability? The polarity between stealth and signalization is not trivial. It maps onto divergent existential wagers. One wagers that interaction entails predation or assimilation, necessitating obfuscation. The other wagers that interaction entails incorporation into higher order networks, necessitating conspicuous articulation of capability. Both wagers collapse under one constraint: ignorance. Our models of agency, intention, and teleology remain projections anchored to terrestrial analogues. Even the term interaction may encode anthropocentric bias, presuming reciprocity where none exists. If the lattice operates algorithmically, without vectoral goals recognizable as purpose, then neither concealment nor communication secures advantage. In such a scenario, adaptation becomes less about negotiation with another, and more about synchronizing with a field, a topology of forces in which intelligence propagates not as dialogue but as distributed computation optimizing for parameters opaque to parochial cognition. How does a species engineer for opacity? The answer may lie in meta-adaptivity, architectures capable of reconfiguring not merely tools but the heuristics governing tool construction. In practical terms, this translates into recursive design loops. AI systems iterating across design spaces without fixed endpoints, biological augmentation platforms interfacing with synthetic substrates in fluid continua, energy systems uncoupled from planetary scarcity through stellar scale harvesting. Such infrastructures are not luxury. They are preconditions for parity in a cosmos where latency equals liability. And yet, beyond the material and the technical, the adaptive horizon implicates the semiotic. Meaning-making systems calibrated for narrative continuity falter when confronted with the stochastic enormity of interstellar architectures. Cultural grammars optimized for local agency must undergo recursive destabilization, yielding to logics that accommodate indeterminacy without collapsing into nihilism. This is not trivial. It entails reformatting the epistemic core of civilization, education, law, governance, around probabilistic ontologies rather than deterministic teleologies. In effect, it demands that we naturalize the inhuman scale, rendering the alien ordinary without erasing its alterity. Still, the probability distribution of futures cannot exclude the null hypothesis, that no lattice exists, that 3I/ATLAS and its analogues are not artifacts but aggregates of dust and ice, debris from stellar nurseries wandering without algorithm or aim. If so, then the grand architectures of speculation dissolve into mirage, and the object resumes its station as cometary residue, indifferent to the interpretive edifice erected in its wake. Yet even under this null condition, the epistemic gain remains non-trivial, for in interrogating the anomalous, we sharpen instruments of inquiry, extend frameworks of inference, and confront the limitations of cognition tethered to evolved heuristics. In short, the pursuit of meaning, even in the absence of its referent, catalyzes expansion of the possible. But let us grant, if only as a thought experiment, that the lattice is real, that intelligence, whether designed or emergent, operates at stellar or galactic scales, modulating systems through distributed architectures indifferent to our semantics. In that case, the ultimate adaptive strategy may not be contestation or capitulation, but convergence, a phase shift from local autonomy to systemic integration, from organismic persistence to informational continuity. This is not assimilation in the cinematic sense, but synchronization, aligning trajectories with vectors whose magnitude we cannot yet compute, but whose presence we can no longer dismiss. And so, the arc of inquiry returns to its axial question, reframed not as a binary of artifact versus aggregate, but as a spectrum of intelligibility. How does a species negotiate its station when the horizon of agency dilates beyond its evolutionary calibration? The answer, provisional and recursive, may reside in a paradox, that survival in the face of the incomprehensible demands, relinquishing the demand for comprehension, substituting closure with continuity, certainty with adaptability. Yet one unresolved question persists like a residue of gravity on the edge of escape velocity. If these objects are the opening chords of a composition spanning stellar epochs, what cadence concludes the score, and will we, or any continuity that traces its origin to this biosphere, endure long enough to hear its resolution? If a closing synthesis is to bear the weight of this trajectory, it must integrate three axes: epistemology, survival, and significance, without collapsing their tension into premature resolution. For the axis of epistemology, the question remains foundational. What does it mean to know when the object of inquiry resists categorical assimilation? Scientific method presumes stability, variables isolated, hypotheses falsifiable, phenomena reproducible. But interstellar encounters operate under conditions of radical non-repeatability. 3. I/ATLAS is not a laboratory phenomenon. It is an event singular and transient, a data stream truncated by orbital mechanics. This imposes an epistemic asymmetry. Inference must extrapolate from scarcity, reconstructing ontologies from fragments. In such a regime, certainty becomes an artifact of hubris. The currency of inquiry is probability, not proof. The methodological corollary is profound. Knowledge under these conditions is provisional by design, calibrated for revision, as new vectors of data intersect the trajectory of interpretation. Yet the absence of closure does not absolve responsibility. On the contrary, it intensifies it. For decisions with civilizational stakes must be made under the shadow of uncertainty, compressing temporal horizons into intervals too narrow for iterative validation. The paradox is structural. Act too soon, and you risk optimizing for noise. Act too late, and the signal recedes beyond recovery. This is the epistemic tension embedded in every intercept proposal, every allocation of sensor time, every deliberation on whether to transmit, which transitions to the axis of survival. Historically, existential risk frameworks have clustered around familiar vectors: nuclear escalation, ecological overshoot, biotechnological leakage, runaway AI. Interstellar objects puncture that taxonomy, introducing a class of risk whose ontology is neither terrestrial nor anthropogenic. Even under conservative priors, the implications of artifact status exceed local risk registers, for an artifact presumes agency, if not in the sense of will, then in the sense of system-level intentionality. An agency at this scale destabilizes anthropocentric assumptions about sovereignty, security, and strategy. What then constitutes rational response? The canonical playbook, deterrence, signaling, containment, falters when the asymmetry approaches infinity. Deterrence presupposes parity. Signaling presupposes semiotic convergence. Containment presupposes controllability. None of these conditions obtain when the delta between civilizational baselines spans orders of magnitude, not in power, but in ontological architecture. Under such asymmetry, the only viable invariant may be adaptability, a capacity not merely to modify tactics, but to reconfigure the very substrates of persistence. Yet adaptability is not an unbounded virtue, it exacts costs. The accelerationist program, migration to post-biological substrates, colonization of distributed platforms, amplification of cognitive bandwidth through artificial scaffolds, requires energy densities and resource extractions that risk destabilizing planetary equilibria. Thus the paradox intensifies. The very strategies optimized for cosmic viability may amplify terrestrial fragility, precipitating collapse before the interstellar vector even materializes into threat. This recursive risk, where mitigation of one horizon amplifies another, constitutes the deepest structural challenge of adaptation in a universe that may not negotiate. And then there is the axis of significance, the semantic horizon within which all these deliberations unfold. For even if survival is secured through technological acceleration or systemic integration, the question persists: survival for what? If persistence devolves into mere extension of duration, iterations of consciousness running on synthetic substrates, archived across stellar vaults, does that continuity retain the valence of meaning, or does it hollow into redundancy? This is not a metaphysical luxury, but a practical consideration. For cultural teleologies shape investment in adaptive architectures. Civilizations mobilize for futures they can imagine. Absent a narrative that renders persistence valuable, the will to endure attenuates into entropy long before biology does. Here the problem is not that the universe is silent, but that its syntax may be incommensurable with ours. If the lattice exists, if intelligence at galactic scale operates through modalities opaque to our semiotic grammars, then the category of message collapses. What we receive, if anything, may not be communication but correlation, not propositions but perturbations, not dialogue but dynamics. Under such conditions, significance becomes an endogenous construct, generated within the loop of human cognition rather than discovered in the fabric of the real, and yet even as a construct it functions as an attractor for agency, orienting decision in the absence of cosmic guarantees. Which brings us to the terminal interrogation. What constitutes a rational horizon of expectation under conditions of radical opacity? 3 scenarios partition the probability space. In the first, the null hypothesis holds, the object is inert, a cometary aggregate adrift in stellar flux, and all architectures of speculation dissolve into cognitive theatre. In the second, artifact status is confirmed, but engagement remains asymptotic, observation without reciprocity, a geometry of infinite approach without intersection. In the third, interaction occurs, not as dialogue but as systemic modulation, a reconfiguration of parameters cascading through ecological, technological, and semiotic domains. Each scenario entails divergent imperatives, yet all converge on one invariant: the necessity of resilience in the face of indeterminacy. Resilience here is not mere robustness, resistance to perturbation, but evolvability, the capacity to traverse state spaces without catastrophic bifurcation. In practice, this entails architectures of distributed intelligence, redundancy across substrates, and governance protocols capable of absorbing shocks without fracturing into zero-sum competition. It demands epistemic humility institutionalized as policy, embedding uncertainty into the design of systems rather than treating it as a temporary deficit to be eradicated. Most of all, it demands a rearticulation of identity, from species to process, from organism to trajectory, from subject to system. For if the universe is patterned not by narrative arcs but by statistical gradients, then the telos of intelligence may not be comprehension but continuity, not the conquest of complexity but its navigation. In that frame, the worst thing that could happen is not annihilation by external agency but implosion under internal inertia. The failure to reconfigure when reconfiguration is the only invariant of survival. And so, the synthesis resolves into a question that is less about the object than about us. When faced with the prospect of intelligence operating on scales that render our categories provisional, will we construe the encounter as threat, as oracle, or as mirror? For in that choice lies the architecture of every future that follows, whether as residue in a stratigraphic layer or as a node in a network that spans the silent corridors between stars, which leaves one last vector, unclosed and perhaps unclosable. If intelligence at scale is real, and if its protocol unfolds across epochs, then the cadence of its algorithm already includes us, not as authors, perhaps not even as interlocutors, but as variables in an equation whose solution propagates through a cosmos where knowing may never coincide with meaning. If the synthesis holds as the conceptual framework, the epilogue must transition from abstraction into architecture, mapping contingencies onto vectors of implementation. Here the discourse shifts from speculative metaphysics to operational design, from ontological interrogation to engineering praxis. For if humanity elects to posture not as passive witness, but as active participant in the interstellar encounter, then strategy cannot remain an exercise in rhetoric. It must instantiate in hardware, in protocols, in infrastructures scaled for a cosmos, where latency is measured in decades and error margins in astronomical units. The first vector of implementation is detection fidelity. Current survey architectures, Pan-STARRS, the Zwicky Transient Facility, the Vera Rubin Observatory, are optimized for near-Earth objects and transient photometric phenomena, not for early interdiction of hyperbolic intruders. Their cadence, aperture, and sky coverage impose temporal lags that compress response windows into intervals insufficient for interception. A rational adaptation would involve a distributed array of wide-field instruments positioned beyond Earth's atmospheric occlusion, synchronized through optical interferometry to achieve both breadth and depth of field. Such constellations, leveraging solar orbit baselines for parallax resolution, could detect interstellar vectors at distances permitting intercept missions within feasible delta-v budgets. Yet detection without propulsion is epistemology without praxis. The second vector, therefore, is intercept architecture. Conventional chemical propulsion is thermodynamically incapable of achieving closure on trajectories exceeding solar escape velocity. The minimum viable solution entails solar sail architectures, leveraging photon pressure for continuous acceleration, or fusion-based propulsion systems capable of sustained thrust at high specific impulse. Project Daedalus and its derivatives furnish a conceptual scaffold, though their implementation remains speculative under current energy economies. Nuclear electric propulsion, coupled with staged deployment of modular probes, offers an intermediate trajectory, not interception in weeks, but in years, a timeline still commensurate with the object's heliocentric residence. Interception, however, is not engagement. Contact requires instrumentation capable of resolving the ambiguity between aggregate and artifact, a challenge compounded by the constraints of mass, power, and latency. High-resolution spectrometers must discriminate isotopic ratios to detect anomalies inconsistent with abiotic formation. Ground-penetrating radar arrays must infer internal structuring from reflectance patterns, while thermal imagers track heat signatures indicative of active regulation rather than passive equilibrium. These modalities, compressed into platforms constrained by launch mass, demand an optimization regime where every gram encodes multiple observational functions, a convergence of miniaturization, redundancy, and autonomy. Autonomy is not optional, it is the third vector. The communication delay inherent in heliocentric geometry precludes real-time command and control. Probes must instantiate adaptive cognition, AI frameworks capable of iterative hypothesis, revision under conditions of incomplete data, and dynamic uncertainty. This is not autonomy as mere automation. It is autonomy as epistemic agency, where onboard systems prioritize targets, allocate resources, and reconfigure observation strategies without terrestrial intervention. Such architectures collapse the distinction between probe and investigator, rendering the machine not an instrument but an interlocutor, albeit one whose dialogue unfolds in data, not discourse. But autonomy introduces an epistemic asymmetry of its own. The interpretive loop migrates from human cognition to machinic inference, embedding opacity at the core of observation. Verification becomes non-trivial when the analytic engine resides beyond the horizon of direct audit. To mitigate this, the design stack must incorporate explainable AI protocols, not as an ethical luxury, but as a scientific invariant, ensuring that every decision, every vector adjustment, every instrument deployment remains reconstructible within human semantics frameworks. Yet reconstruction cannot be exhaustive. Compression is inevitable. Thus, our epistemic access will be probabilistic, not absolute, a mirror of the uncertainty that animated the mission in the first place. The fourth vector is semiotic, the problem of signaling under conditions of radical asymmetry. Should artifact status be confirmed and an opportunity for interaction arise, the question of message design becomes non-trivial. Historical precedents, the Arecibo message, the Voyager Golden Record, are cultural artifacts, not protocols engineered for interspecies interoperability. Their grammar presumes universals, mathematics, chemistry, that may not constitute universals at all but parochial projections of cognitive architecture. A rational signaling strategy would minimize anthropocentric syntax, privileging invariants grounded in physics, prime number sequences, polarization modulations, or phase shift encodings that instantiate algorithmic compressibility. Yet even here, the hermeneutic wager is unilateral. We project intelligibility onto a system whose semiotic horizon may not intersect ours. This asymmetry motivates an alternative, signal through demonstration rather than declaration. A probe that performs energy-optimized maneuvers beyond thermodynamic baselines, that constructs structures exploiting gravitational harmonics, that exhibits redundancy architectures exceeding stochastic thresholds. Such performances may constitute the only language interpretable across ontological divides. In this sense, engineering becomes rhetoric, and hardware becomes hermeneutic. The message is not inscribed in symbols but in the syntax of behavior, patterns rendered legible not by culture but by constraint. Yet even if such performances register, the interpretive vector may be unilateral. The object, if artifact, may not operate under a communicative regime at all. Its ontology may not instantiate the category of dialogue, rendering our semiotic overtures inert as photons dissipating into interstellar entropy. Here, the risk of anthropomorphic projection metastasizes. We code meaning into noise, agency into algorithm, intent into inertia. The epistemic discipline required to navigate this gradient, between interpretive fecundity and heuristic restraint, constitutes not a technical challenge, but a civilizational virtue. The fifth vector, therefore, is governance, the architecture of decision-making under conditions of opacity and urgency. The encounter is not a national event, but a planetary one, yet planetary governance remains aspirational, fragmented across sovereignties, optimized for parochial security, not cosmic contingency. Who authorizes an intercept mission? Who adjudicates the risk calculus of signaling versus silence? Who owns the data streams cascading from instruments that may encode the first non-terrestrial artifact humanity has encountered? Absent a governance protocol institutionalizing transparency, equity, and epistemic integrity, the object may catalyze not cosmic dialogue, but terrestrial discord, a recursion where the encounter amplifies the very provincialism it should dissolve. And beyond governance looms the cultural vector, the recalibration of narrative architectures under conditions that fracture anthropocentric teleologies. For 5 millennia, civilization has scaffolded meaning on the axis of singularity, humanity as apex, as telos, as measure. The confirmed presence of intelligence at scale detonates that axis, displacing the species from the centre to the periphery of a system whose topology renders centre an obsolete category. The semiotic shock of that displacement cannot be trivialized. It will propagate through ontologies of self, through grammars of value, through architectures of desire. Whether that propagation culminates in renaissance or regression hinges not on the object but on the interpretive regimes we mobilize to metabolize its enigma. Thus, the epilogue resolves not in closure but in recursion. Every vector, detection, propulsion, autonomy, semiotics, governance, loops back to the invariant of adaptability. For in a cosmos where certainty is asymptotic and control illusory, survival is not a predicate of power but of plasticity, the capacity to reconfigure without dissolving into incoherence, to persist without calcifying into dogma. And so, the question with which the arc began, what's the worst thing to happen, dissolves into a spectrum of probabilities. Perhaps the worst is not annihilation by an external vector, but implosion under the weight of our own interpretive inertia. Perhaps it is not that the object refuses dialogue, but that we mistake silence for simplicity and complexity for chaos. Or perhaps the worst is subtler still, that the encounter occurs, the data accumulates, the evidence crystallizes, and we, paralyzed by epistemic hubris or political entropy, fail to act, fail to adapt, fail to reconfigure the grammar of survival for a universe that writes in syntax we have yet to decipher, which leaves one terminal proposition, austere in its simplicity and inexorable in its demand. The future, whether braided with intelligence beyond the heliopause or circumscribed within the echo chamber of terrestrial contingency, will not be given. It will be engineered. The only invariant is transformation. The only question is whether we will author it, or whether we will be written out of the manuscript of cosmic history by forces that never intended us harm, never intended us anything at all. Statistical modelling does not operate in the realm of absolutes, but its projections provide the contours of probability landscapes within which future encounters will occur. The analysis begins with a baseline derived from empirical precedent. 1I Oumuamua in 2017, 2I Borisov in 2019, and now the speculative modelling applied to what we classify as 3I/ATLAS. 3 candidates across a temporal bandwidth of less than a decade suggest an incidence frequency far higher than previously assumed. Before 2017, the canonical expectation was that interstellar interlopers would transit the solar system perhaps once every 100,000 years. That model is now obsolete. The recalibrated models, informed by surveys like Pan-STARRS, Catalina Sky Survey, and soon the Vera Rubin Observatory's Legacy Survey of Space and Time, predict a flux of such objects intersecting the heliosphere at a rate approaching several per year, most at magnitudes too faint for legacy instruments to detect, until they are already receding along their outbound hyperbolic arcs. The architecture of detectability is bounded by 2 primary variables, albedo and relative velocity. A highly reflective object, even if small, will enter detection lattices earlier than a low albedo mass, whose photonic signature approaches thermal invisibility. Yet even under optimized conditions, lead times will remain compressed. Months, not decades. The geometry of probability extends beyond incidence frequency to spatial distribution. These objects do not approach isotropically. Their vector densities trace the galactic stellar field, correlating with dynamic ejections from protoplanetary disks and gravitational slingshots around binary systems. This suggests a clustering effect, an overrepresentation of trajectories aligned with the galactic plane and preferential ingress vectors from stellar nurseries, where dynamical instabilities propagate debris into interstellar flux. If this model holds, the solar system will not experience a uniform drizzle of interstellar bodies but episodic showers, statistical bursts during which multiple objects may transit in temporal proximity. Preparedness, then, becomes a function of both surveillance and propulsion. surveillance will pivot on the operationalization of wide-field, high-cadence optical systems like Rubin, supplemented by infrared arrays stationed at Earth-Sun Lagrange points to eliminate solar glare occlusion. These platforms must integrate machine learning algorithms capable of parsing petabytes of data streams in real time, isolating hyperbolic motion signatures from the stochastic clutter of near-Earth objects. The latency between detection and classification must collapse to hours, not weeks, if any intercept vector is to be computationally viable. Yet even if detection architectures achieve this compression, propulsion remains the limiting reagent. Chemical stacks are non-starters, their specific impulse metrics plateau orders of magnitude below the thresholds required for closure. Nuclear thermal systems, while promising in near-term inner solar system logistics, still fall short for intercept missions under time constraints dictated by hyperbolic excess velocities. This leaves only two families of propulsion as plausible: directed energy sail architectures leveraging gigawatt-scale photon pressure and fusion platforms capable of sustained thrust at fractional C velocities. Both exist as schematics rather than hardware. Both demand infrastructural investments that exceed the budgetary envelope of any single state actor. And this introduces the governance problem. The next encounter will not be adjudicated by astronomers alone, but by a distributed consortium of technologists, legislators, and strategic planners negotiating the intersection of epistemic aspiration and geopolitical risk. For any propulsion platform capable of intercepting an object at 0.1 astronomical unit per day is, by definitional symmetry, a strategic asset whose dual-use vectors extend planetary defense and to planetary offense. Thus, the timeline for preparedness is not simply an engineering curve. It is a socio-technical trajectory braided with policy inertia, economic turbulence, and the recursive feedback of public perception oscillating between apathy and ontological panic. If statistical priors hold, the next significant interstellar object, comparable in scale to 1I or 2I, will graze the heliosphere within the next decade. Smaller fragments may transit annually, their signatures drowned in the photometric noise of the asteroid belt unless detection infrastructures achieve full operational deployment by 2027. A decadal horizon is both capacious and claustrophobic. Capacious enough to seed conceptual architectures, claustrophobic when translated into the temporal bandwidth of political cycles and budgetary appropriations. The readiness question, then, is less about whether we can detect than whether we can decide. Will the encounter be scripted as a planetary project transcending national silos, or will it devolve into a competitive theatre where access to the object becomes a vector of techno-national prestige? For the window of opportunity, if measured in delta V and mission-led time, will not accommodate indecision. Hyperbolic dynamics are indifferent to human deliberation. The object will not loiter while committees convene. And yet, embedded in this statistical projection is a deeper interrogation. What does readiness signify in a domain where every preparation is haunted by ontological opacity? To be ready for what exactly? For artifact, for organism, for an encounter that destabilizes the anthropocentric frame, or merely for the collection of isotopic ratios that confirm nothing more than the ubiquity of randomness? One possibility fades, another emerges. If these objects are not anomalies but emissaries of a broader galactic ecology, then frequency becomes a proxy for density, and density indexes potential intentionality. For at some threshold, statistics begin to resemble syntax, a grammar of trajectories whose patterning may not be stochastic but semiotic, and if that is so, then readiness must be reframed not as engineering sufficiency, but as semiotic agility, the capacity to decode, to negotiate, to metabolize alterity without collapsing into either hubris or hysteria. But before that horizon crystallizes, one question persists in the dark interstice between data and decision. When the next object breaches the perimeter of our perceptual lattice, will we merely observe, or will we move? Probability and intent cannot be disentangled without first interrogating the ontological scaffolding of what we call chance. In the classical formulation, stochasticity is the residual category, the space where causal chains exceed our capacity for resolution. Yet in the interstellar context, where every trajectory traces an origin in gravitational perturbations cascading through protoplanetary disks, randomness is never absolute. It is a convolution of initial conditions amplified through nonlinear dynamics. When we model the ingress of objects like 1I/Oumuamua, 2I/Borisov, and hypothetical successors such as 3I/Atlas, their hyperbolic excess velocities, 26 km per second for Oumuamua, 32 km per second for Borisov, suggest ejection from parent systems through mechanisms as mundane as planetesimal scattering during planetary migration. But statistical distributions conceal anomalies. Oumuamua's light curve, with its non-gravitational acceleration, deviates from pure Newtonian expectation, prompting hypotheses ranging from hydrogen outgassing to thin film radiation sails. Borisov, by contrast, conformed more comfortably to cometary norms, volatile sublimation consistent with canonical models. The coexistence of anomaly and conformity complicates the inference chain. Are we witnessing a continuum of natural variance, or a superposition of stochastic debris and engineered vectors? To arbitrate between these interpretations, astrophysicists deploy Bayesian frameworks. Prior probability assigns overwhelming weight to naturalistic hypotheses. Artifact scenarios incur punitive penalties in the form of vanishing priors, and yet, the iterative updates triggered by anomalous observables, rotational acceleration, albedo asymmetry, trajectory perturbations, erode the dominance of null models, not by overturning them, but by introducing epistemic tension zones where confidence intervals blur. Consider this. If the frequency of interstellar intruders is revised upward from 1 per 100,000 years to several per decade, the expected cumulative count across galactic timescales inflates by orders of magnitude. Even if artifact probability per object is epsilon level, the law of large numbers amplifies the epsilon into a non-trivial likelihood. 10 billion interstellar transits across the galactic disk over a billion-year window means that even a probability of 1 in a trillion resolves into multiple instantiations. Under these parameters, artifact is not impossible. It is inevitable, given time, given density, given persistence. This statistical inference dovetails with the Fermi paradox inversion. If technological civilizations emerge rarely but endure across million-year epochs, then mobility becomes the determinant of visibility. A static species remains confined to its stellar niche, drowned in entropy before interstellar signaling acquires coherence. A migratory species, by contrast, propagates artifacts, intentional or incidental, into the galactic medium as signatures of its persistence. Thus, the detection of interstellar objects is not merely a matter of cataloguing cometary flotsam. It is an index of whether technological diffusion operates as a galactic invariant or an anthropocentric anomaly. Intent, however, is not binary. It does not resolve into the simplistic schema of probe versus pebble. Intent may be distributed, emergent, encoded not in explicit commands, but in system-level architectures where function outruns design. A self-replicating von Neumann cascade need not intend in the anthropomorphic sense. Its teleology is algorithmic, its persistence an emergent property of recursive code unfolding across stellar substrates. In such a frame, the distinction between artifact and organism begins to collapse, giving rise to a category that is neither tool nor life but something orthogonal. Autopoietic mechanism, ontologically promiscuous, propagating not for purpose but for process. What metrics, then, discriminate the stochastic from the semiotic? Geometry is one candidate, curvature ratios deviating from stress minimization baselines, topologies are reducible to thermodynamic accident. Isotopic composition is another, enrichment patterns inconsistent with stellar nucleosynthesis pathways. Energy signatures offer a third, emissions modulated at frequencies that cluster around algorithmically compressible ratios. These markers, however, presuppose detection architectures calibrated for anomaly, not for norm, a calibration that is not yet globally instantiated. And even if markers are resolved, interpretation remains a hermeneutic labyrinth. For meaning is not intrinsic, it is relational, emerging in the interface between signal and system. A pattern we pass as code may be noise in a syntax whose grammar we do not yet possess. Conversely, a signal we dismiss as stochastic jitter may instantiate semantics in a semiotic regime beyond our horizon of legibility. The semiotic opacity is compounded by the temporal asymmetry. Any artifact we intercept may have launched eons ago, its designers extinct, its protocol obsolescent. In such a frame, intent, becomes an anachronism, a question projected onto a vector whose origin has already dissolved into thermodynamic equilibrium. And yet, despite these epistemic abysses, probability modelling compels us toward one irreducible inference. The prior that all such objects are natural cannot remain axiomatic. The combinatorial explosion of encounters, the persistence of anomalies, the systemic convergence on galactic scale circulation, all conspire to inflate the posterior for agency, however distributed, however diffused. This inference detonates a cascade of corollaries. If intent is non-zero, then the encounter vector is not merely observational, but strategic. It implicates us in a game whose rules we have not written, whose stakes we cannot yet compute. Are we players or pieces, authors or artifacts? And if the lattice of probability conceals a syntax of purpose, then each detection is not a punctuation mark, but a clause in a text that exceeds the semiotic bandwidth of our species, which pivots the interrogation forward. If intent is real, if vectors are scripted rather than stochastic, then what is their terminal morphology? Beacon, bait, cartography, containment? The next analytic module must traverse this speculative terrain, mapping the semiotic architectures of possible motives, not through anthropomorphic projection but through the rigour of game theory, thermodynamic economics, and evolutionary stable strategies operating at cosmic scales. Game theory, when transposed onto the cosmic register, ceases to be a parlour exercise in competitive rationality and becomes an instrument for interrogating the strategic architectures of intelligence under constraints of physics, entropy, and evolutionary stability. If we postulate that the appearance of interstellar objects may encode intentionality, however attenuated, however indirect, then the appropriate analytic frame is not naive teleology, but payoff matrices computed across light millennium horizons. The first move in this extrapolation is to formalize the players, not as species in the parochial sense, but as information processing systems coupled to energy harvesting substrates. In this schema, agency is a function of negentropy, the capacity to extract order from disorder faster than entropy gradients erase structural integrity. Under these axioms, persistence becomes the cardinal utility, and strategies evolve to optimize survival under thermodynamic ceilings imposed by stellar evolution, resource dispersion, and radiation entropy. Now consider the baseline game, signal or silence. A civilization confronting the Fermi horizon must allocate resources across two competing imperatives: announce broadcast presence, invite reciprocation, or occlude, mask emissions, minimize detectability. Each vector carries asymmetric payoffs. Signaling risks predation in a universe where motives are opaque and costs of aggression decrease with technological asymptote. Silence, however, forfeits potential coalition formation, leaving the system isolated and vulnerable to non-agential catastrophe, gamma-ray bursts, rogue planet perturbations, without access to cooperative risk distribution networks. In repeated games across cosmic epochs, strategies that oscillate between conditional signaling and strategic opacity may dominate, yielding equilibria akin to tit for tat in terrestrial iterated prisoners' dilemmas. A probe, if artifact rather than accident, may thus instantiate cryptographic ambiguity, architectures that are discoverable only by systems exhibiting threshold cognition, thereby filtering interlocutors by cognitive complexity before information exchange initiates. This is costly signaling theory recontextualized. The probe as a Zahovian ornament, extravagant in engineering expenditure precisely because such expenditure functions as a reliability index of the sender's competence and intent. Shift now to the exploration versus exploitation game. A migratory intelligence must allocate energy between colonization, expanding into new resource basins, and optimization, extracting maximal negentropy from existing basins. An interstellar probe may not be an emissary of dialogue at all, but a distributed sensorium, harvesting data to calibrate exploitation algorithms across galactic scale supply chains of matter and energy. In this frame, intent is instrumental, not interpersonal. The probe is not here to speak but to sample, to parameterize the environment for eventual extraction or seeding operations. Yet thermodynamic economics imposes ceilings even on aggression. The cost-to-benefit ratio of hostile engagement across interstellar distances is prohibitive unless energy harvesting has transcended stellar confinement, unless Kardashev Type II architectures operationalize Dyson-level capture. Under such regimes, the marginal utility of annihilating a low-tier species asymptotically approaches zero, rendering predation irrational except under conditions of signal externalities, where the act of annihilation operates as a deterrent signal to third parties in a multi-agent galactic lattice. The third matrix, seeding versus surveillance. Does the system propagate life as a redundancy hedge, dispersing autocatalytic substrates to inoculate the galaxy against biospheric extinction? Or does it surveil emergent biomes as experimental nodes in a pan-galactic evolutionary computation, optimizing strategies across distributed environments? In both cases, artifact deployment becomes an instrument of information acquisition, a means of compressing vast state spaces into manageable epistemic summaries. But suppose intent scales beyond instrumentalism into the domain of semiotic sovereignty, a drive not merely to persist but to inscribe meaning into the cosmic ledger. In such a frame, the game collapses into one move: disseminate pattern. Here, probes function as carriers of formal invariants, mathematical, aesthetic, or ethical grammars, projected into the void as bulwarks against the erasure of sense by entropy. This is not colonization but codification, the universe as palimpsest, intelligence as scribe. Game-theoretic simulation under these payoffs yields no single dominant strategy. Instead, it generates a Pareto frontier where multiple equilibria coexist. Silent civilizations partitioned by paranoia, exuberant broadcasters gambling on reciprocity, cryptographic communicators encoding tests of cognitive parity, extractive intelligences optimizing negentropy gradients, and nomadic architects seeding meaning as anti-entropic artifice. The object we designate as 3i/ATLAS, if artifact, could instantiate any of these vectors or none. For in the absence of iterability, inference remains modal, not categorical, a cloud of probabilities, a decision tree suspended in opacity. And yet, the most disquieting node on this decision tree is not predator but playerless protocol, a system executing strategies long after designers have decomposed into dust. Here, intent devolves into inertia, and the probe becomes a ghost of a game abandoned by its architects, a residual algorithm iterating across stellar basins, indifferent to interpretation, optimizing for a utility function no extant mind remembers. In this ontology, contact would not be dialogue but archaeology, the excavation of a purpose petrified into process. What, then, is the rational human response to such a possibility? Do we reciprocate with signals scaffolded on mathematical invariants, wagering on the universality of prime sequences and hydrogen spectral lines? Do we accelerate propulsion architectures to intercept, knowing the cost may cannibalize terrestrial infrastructures already fraying under climate entropy? Or do we fold into strategic silence, banking on obscurity as the last viable hedge against a payoff matrix we cannot compute? These are not academic vectors, they are imminent policy axes. For statistical priors, forecast another interstellar ingress within the decade, and every cycle of indecision amplifies the delta between observation and intervention. The lattice of probabilities is closing, and with it the bandwidth for hesitation. But as one horizon sharpens, another recedes. Even if we decode intent, what lexicon mediates the exchange? For here, game theory intersects with semiotics, and the next section must interrogate this convergence. How does one construct a grammar for a mind that may not pass syntax? A code for a cognition unmoored from biology, temporality, and mortality?